What lies beyond the horizon of our observable universe? Is it an endless expanse, brimming with unexplored worlds and unseen galaxies? Or could it be a place where parallel universes and new dimensions exist, waiting to be discovered? Perhaps it holds the origins of mysterious cosmic events that have eluded our understanding for millennia. Join us on an extraordinary journey as we venture into the unknown, questioning the very nature of the universe and what might lie just beyond the edge. The universe, an incomprehensible sea of space, time, matter, and energy, stretches across dimensions we are only beginning to grasp. From the most infinitesimal subatomic particles to the colossal clusters of galaxies, the universe weaves an intricate tapestry of existence. It's a cosmic stage where forces as old as time itself play out, shaping everything we see around us. The very fabric of the universe spans tens of billions of light years across, a vast expanse that continues to grow and expand since the Big Bang, approximately 13.88 billion years ago. But what does this expansion truly mean? The universe itself is stretching. Galaxies are racing away from each other at speeds that can even exceed the speed of light. This mind-boggling phenomenon is driven by dark energy, a mysterious and invisible force that makes up around 70% of the universe's total energy content. Alongside dark matter, which accounts for roughly 27%, these unseen and largely enigmatic forces govern the very structure and evolution of the cosmos. They affect how galaxies form, how stars evolve, and even how the universe itself will ultimately end. Within this vast cosmic expanse, galaxies act as islands, each one an intricate system of stars, planets, black holes, and nebulae. Our own Milky Way galaxy, a stunning spiral of stars and celestial wonders, houses more than 100 billion stars. Each of these stars could potentially have planetary systems orbiting them, just as we orbit our sun. The force of gravity is the invisible conductor, orchestrating a cosmic ballet where stars and galaxies are bound together, pulled toward the center of mass, and move through the universe in ways we are only beginning to understand. Yet the universe isn't merely a place of delicate order. It is also a place of violent change and destruction. Stars explode in supernovae, black holes devour everything in their path, and high-energy cosmic rays streak through the void at nearly the speed of light. In the midst of this chaotic dance, the universe constantly balances creation, forging new elements, new stars, and new worlds, even as it tears down the old. This push and pull between creation and destruction is the very heart of the cosmos, a dynamic process that fuels the ever-changing nature of the universe. So what about the edge of the universe? How can we even begin to grasp the concept of something so vast, so incomprehensible? Scientists do not think of the edge of the universe as a physical boundary. Instead, they imagine it as the limits of our observational capacity. The observable universe is essentially defined by how far light has had time to travel since the Big Bang. Right now, this distance extends across a spherical region approximately 93 billion light years in diameter. And that is just the observable universe, the region from which light has had time to reach us. Beyond this horizon lies the vast expanse of unobservable space, forever out of reach due to the finite speed of light and the ever-accelerating expansion of the universe itself. Astronomers use incredible tools to peer deeper into this cosmic mystery. The Hubble Space Telescope, which has captured images of galaxies billions of light years away, is one of the instruments that has brought the most distant corners of the universe into view. Now, the James Webb Space Telescope promises to offer even clearer insights into this cosmic puzzle, delving into galaxies that existed when the universe was only a few 100 million years old. Even more fascinating is the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation, invisible to the naked eye but detectable by sensitive instruments, provides a glimpse of the universe's infancy, marking the oldest light we can detect. But these efforts only scratch the surface of what exists beyond the observable universe. There lies a vast hidden cosmos, unreachable and beyond our current understanding. The universe, in its unobservable vastness, remains a place of profound mystery and awe. What lies beyond the light we can see? What secrets are hidden in the dark expanses of space that we can only imagine? As we attempt to understand this enigmatic edge, it's important to realize that the edge isn't a finite boundary. It's a constantly shifting horizon, ever expanding as light from farther objects has more time to reach us. Each moment, the observable universe grows, revealing more of the mysteries that lie in its depths. But beyond that horizon, the unobservable universe remains a place of infinite possibilities, a realm that stretches far beyond the reach of our current understanding. The universe is much more than the sum of its observable parts. It is a living, breathing entity, constantly evolving, expanding, and changing. Whether there are other dimensions, parallel universes, or entirely new realms of existence beyond the observable universe is a question that continues to spark the imagination of scientists and dreamers alike. What is certain is that the universe, in all its wonder, will continue to reveal itself piece by piece as we continue our journey through the cosmos. So what do you think lies beyond the edge of the observable universe? Could it be new worlds, hidden realms, or something even more extraordinary? The only way to find out is to keep exploring, to keep asking questions, and to keep looking up at the stars. Over billions of years, the observable universe has unfolded as an ever-expanding frontier, revealing more about the realms beyond and the very fabric of existence. The sheer vastness of this observable universe is staggering, with an estimated diameter of around 93 billion light years. To grasp this immensity, consider that traveling at the speed of light, an unfathomable 300,000 kilometers per second, would still take 93 billion years to journey from one edge of the observable universe to the other. And yet, this is merely the observable portion. The universe we can see is just a small slice of a much greater expanse, one that may be far larger, potentially infinite. Within this colossal span of space lie billions of galaxies, each teeming with millions to trillions of stars. Countless planets orbit these stars, many of which remain undiscovered. And yet, despite these overwhelming distances, it's important to remember that the observable universe is only that, what we can currently detect with our instruments. Beyond that observable edge, the true universe may extend far beyond our capacity to observe, opening up possibilities we can only imagine. The scale of this vast universe is best understood through comparison. For example, our Milky Way galaxy, which seems vast to us, spans about 100,000 light years in diameter. In the context of the observable universe, however, it is merely a tiny dot, lost in the vastness of space. Even larger structures, such as the Virgo supercluster, which contains the Milky Way, become mere specks within the greater cosmos. The cosmic microwave background, CMB, the oldest detectable light, helps us understand the universe's origins by mapping the universe as it appeared about 380,000 years after the Big Bang. This ancient light provides a window into the universe's vastness and its incredible age, offering a glimpse into a time long before humanity could even comprehend such a scale. As our technological and scientific capabilities evolve, so too does our understanding of the universe. Current cosmological theories center around two major possibilities regarding the universe's true size, whether it is finite but unbounded or infinite. The finite but unbounded model offers an intriguing analogy. Just as the surface of a sphere is finite yet has no edges, the universe could be a three-dimensional space that loops back on itself. In this scenario, one could theoretically travel in a straight line and return to their starting point. This idea aligns with Einstein's theory of general relativity, which describes gravity and the fabric of space-time. However, this doesn't necessarily mean the universe is small. On the contrary, it could be unimaginably vast, even if it is finite. Alternatively, the infinite universe model suggests space stretches endlessly in every direction. This idea finds support in both observational data and mathematical models, particularly the flatness of the universe on large scales. A flat universe with zero curvature implies that space may extend indefinitely, without boundaries. Measurements of the cosmic microwave background radiation provide further evidence for this notion, showing that the observable universe is remarkably uniform and isotropic. If the universe is indeed flat, it's plausible that it stretches forever, beyond the limits of our observation. Both models offer tantalizing insights into the nature of the cosmos, but each raises profound questions that challenge our understanding of reality. A finite but unbounded universe presents mysteries related to the topology geometry of space itself. An infinite universe, on the other hand, forces us to confront the very concept of infinity, an idea that has baffled mathematicians and philosophers for centuries. As scientists continue to gather data and refine our theories, these possibilities remain at the forefront of cosmological research, beckoning us to explore the ultimate truth of the universe's true scale and nature. Moreover, the true scale of the universe remains shrouded in mystery, as our observations are confined to the observable universe, a small fraction of what may exist beyond our current reach. What lies beyond this boundary, whether it is additional galaxies, alternate physical laws, or even entirely separate universes, is still the realm of theoretical speculation. It is only through future discoveries and advancements in technology that we may begin to uncover the vast expanse that stretches far beyond what we can see today. The Big Bang Theory, the dominant scientific explanation for the origin and early development of the universe, posits that the cosmos began as an incredibly hot, dense point roughly 8 billion years ago. This initial singularity held all the matter and energy that would eventually form galaxies, stars, planets, and everything we see around us today. The term Big Bang, however, can be somewhat misleading, as it doesn't describe an explosion in space. Instead, it refers to the rapid expansion of space itself from this initial state. As the universe expanded, it began to cool and become less dense over time, setting the stage for the formation of the first structures of the universe. In the first fractions of a second after the Big Bang, the universe underwent a dramatic phase of expansion known as cosmic inflation. During this brief but intense period, the universe expanded exponentially, smoothing out irregularities and preparing the groundwork for the large-scale structures that would eventually form. Once inflation ended, the universe continued to cool, allowing subatomic particles to come together and form the simplest of atoms. Approximately 380,000 years later, the universe had cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This event, known as recombination, marked the point at which the universe became transparent to radiation, releasing the faint cosmic microwave background, CMB, radiation that still permeates the universe today. The CMB serves as a snapshot of the infant cosmos, providing a unique glimpse into the early stages of the universe. Over the course of billions of years, gravity worked its magic, pulling matter together to form the stars, galaxies, and even the vast clusters of galaxies that populate the cosmos. Observations of distant galaxies reveal that they are moving away from us, a phenomenon that further underscores the idea that the universe is still expanding. This ongoing expansion is attributed to the influence of dark energy, a mysterious force that makes up roughly 70% of the universe's total energy content. Despite its pervasive presence, dark energy remains one of the greatest mysteries in modern physics. The evidence supporting the Big Bang Theory is vast and compelling, with several key observations reinforcing its validity. Among the most persuasive pieces of evidence is the cosmic microwave background radiation, first discovered in 1965 by Arno Penzias and Robert Wilson. This faint glow, which fills the universe, is the afterglow of the Big Bang itself. It provides a snapshot of the universe at around 380,000 years after its birth, when it had cooled enough for atoms to form. Subsequent precision measurements of the CMB, particularly through missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have provided us with a detailed map of temperature fluctuations that align perfectly with the predictions made by the Big Bang model. Another strong piece of evidence comes from the observed abundance of light elements like hydrogen, helium, and trace amounts of lithium. These elements were created during a period known as Big Bang nucleosynthesis, which occurred just minutes after the Big Bang. During this brief period of intense heat and density, protons and neutrons fused to create the light nuclei that make up much of the observable universe. The observed ratios of these elements in the cosmos today perfectly match the predictions made by the Big Bang Theory, offering further confirmation of its accuracy. Finally, the discovery of the redshift of distant galaxies provides dynamic proof of an expanding universe. In the 1920s, Edwin Hubble observed that galaxies were moving away from us in all directions, with their light stretching to longer, redder wavelengths as they receded. This redshift phenomenon fits perfectly with the idea of a universe that started from a hot, dense point and has been expanding ever since. The farther a galaxy is, the faster it appears to be moving away, further supporting the notion of a singular cosmic origin. When combined, these lines of evidence form a coherent and compelling picture of the universe's origin, evolution, and continuing expansion. The Big Bang Theory offers an elegant explanation for the birth of the universe from a singularity, an infinitely small, hot, and dense point, approximately 13.8 billion years ago. Far from an explosion in space, the Big Bang was an expansion of space itself, setting in motion the processes that would eventually give rise to the vast complex cosmos we observe today. This theory is not only a framework for understanding the past, but also a guide for future discoveries that may help us uncover even more about the universe's origins, its present state, and its ultimate fate. The expansion of the universe from a singular point marks the birth of everything we know. From this unimaginable beginning, the cosmos stretched out into the vast, ever-expanding space that continues to grow and evolve. At the very start, the universe was a searing cauldron of extreme heat and density, so intense that particles and forces as we understand them today had yet to take shape. In fact, during the first moments, the universe underwent a dramatic phase known as cosmic inflation. This rapid expansion, faster than the speed of light, flattened and smoothed any irregularities from the initial state, creating the foundation for the massive cosmic structures we observe today, like galaxies and clusters of galaxies. As the universe cooled, matter began to form. Subatomic particles first emerged and then bonded to create the simplest elements, primarily hydrogen and helium. This cooling process reached a pivotal moment roughly 380,000 years after the Big Bang, an event we now refer to as recombination. During this critical phase, electrons and protons united to form neutral hydrogen atoms, allowing the universe to become transparent to radiation. The result of this event is the cosmic microwave background, CMB, a faint afterglow of the Big Bang that we can still detect. The CMB is like a snapshot from the distant past, a relic of a time when the universe transitioned from a hot, dense plasma to a transparent cosmos that set the stage for everything that came afterward. Following this phase, the universe's cooling continued, and small fluctuations in the density of matter from the early universe slowly grew into the stars and galaxies we recognize today. These stars, which evolved and eventually exploded in supernovae, seeded the cosmos with heavier elements crucial for the formation of new stars, planets, and life itself. Our very own solar system, born from this cosmic recycling, is part of a larger cosmic narrative that stretches back billions of years. The Big Bang Theory, supported by several key pieces of evidence, such as the CMB, the distribution of light elements, and the observable redshift of galaxies, provides a robust framework for understanding the origins and evolution of the universe. It paints a picture that stretches from the incomprehensibly hot and dense beginnings to the universe as we experience it today, a place that is still expanding and evolving in ways that remain beyond our complete grasp. Despite this, one of the biggest mysteries in cosmology remains the conditions before the Big Bang. The singularity, the point from which the Big Bang emerged, defies our conventional understanding of physics. Thought to have been infinitely small and dense, it housed all the matter and energy that would later become the universe. In this extreme state, the established laws of physics, such as general relativity and quantum mechanics, break down. This breakdown leads to profound questions about what happened before the Big Bang, especially since time itself, along with space, came into existence at the moment of the Big Bang. In essence, the very concept of before the Big Bang becomes meaningless in the classical sense. One of the more provocative ideas that have emerged in the scientific community is the multiverse theory. This hypothesis suggests that our universe may not be a solitary event, but rather one of many universes, each potentially governed by its own set of physical laws. Some versions of this theory even propose a cyclical universe, where each Big Bang is followed by a period of expansion, eventual contraction, and a big crunch, which would then spark a new Big Bang. If this cyclical model is correct, it implies an eternal series of cosmic cycles, eliminating the need for a true beginning or an end. Further avenues of inquiry focus on quantum gravity theories, such as loop quantum gravity, which seek to reconcile the fundamental principles of general relativity with the quantum mechanics that govern the very small. Some of these theories suggest that the singularity from which the Big Bang emerged may have been a quantum event, replaced by a quantum bounce. This idea proposes that the universe may have undergone a previous phase of contraction, leading to the Big Bang and the expansion we observe today. While these speculative ideas remain highly theoretical, they provide a tantalizing glimpse into possible scenarios that could explain the nature of the universe before the Big Bang. Though we lack empirical evidence to support them, these theories challenge our deepest understandings of space, time, and the very fabric of the universe itself. As research progresses, we may eventually uncover new insights that could forever alter our comprehension of the cosmos, shedding light on the mysteries of existence and our place in it. The questions surrounding the origins of the universe and the conditions before the Big Bang continue to captivate the imagination of scientists and lay people alike. Through the lens of theoretical physics and cosmology, we inch ever closer to understanding the complexities of the universe, perhaps someday unlocking the secrets of time and space. The journey, however, is far from over, and as we look to the stars, we remain on the cusp of an ever-expanding quest for knowledge. Scientists are investigating the early moments of the Big Bang using a blend of observational astronomy, particle physics experiments, and advanced computer simulations. One of the most vital tools in this groundbreaking endeavor is the cosmic microwave background, CMB radiation, essentially the faint afterglow of the Big Bang. By meticulously observing and analyzing the CMB, scientists gain a deeper understanding of the universe's conditions when it was just 380,000 years old, a mere fraction of its current age. Instruments such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have mapped the subtle temperature fluctuations in the CMB with astonishing precision. These fluctuations offer invaluable insights into the universe's initial conditions, its rate of expansion, and the distribution of matter and energy. By unraveling the mysteries contained within the CMB, scientists piece together the cosmic puzzle and reveal the birth of our universe. However, studying the early universe goes beyond just observing radiation. Particle physics plays a crucial role as well. Facilities like the Large Hadron Collider, LHC, at CERN recreate the extreme conditions that existed just moments after the Big Bang. By colliding particles at incredibly high energies, these experiments simulate the state of the universe just after its birth. In doing so, they test theoretical models and investigate phenomena like the Higgs boson, which explains how particles acquire mass. Such discoveries provide indirect evidence about the universe's state in its infancy, validating the predictions made by cosmological models. Moreover, computer simulations and theoretical models are indispensable in understanding the evolution of the universe. By feeding observational data and fundamental physical laws into supercomputers, scientists can simulate the universe's development from the Big Bang onward. These simulations test hypotheses about processes such as cosmic inflation, nucleosynthesis, the formation of light elements, and the birth of large-scale structures like galaxies and galaxy clusters. Comparing these simulations with real astronomical observations enables scientists to refine their theories, ultimately providing a clearer picture of the complex dynamics that shaped the universe in its earliest moments. Together, these approaches, studying the relic radiation of the Big Bang, recreating high-energy environments in particle accelerators, and running detailed simulations, form a comprehensive strategy that allows scientists to reconstruct the intricate puzzle of the universe's origins. Through this multifaceted approach, they continue to uncover the fundamental processes that set the stage for everything we observe in the cosmos today. One of the most important concepts in cosmology today is the theory of cosmic inflation. This groundbreaking theory describes an explosive period of rapid exponential expansion in the universe's first fraction of a second. According to the inflationary theory, this rapid expansion took place approximately between $10 minus $36 to $10 minus $32 seconds after the initial singularity. During this brief moment, the universe stretched by a factor of at least 10^26, smoothing out irregularities and setting the stage for the homogeneous and isotropic universe we observe today. The theory of cosmic inflation, first proposed by physicist Alan Guth in 1980, was developed to address several fundamental problems with the traditional Big Bang theory. One of the most notable issues is the horizon problem, which asks why distant regions of the universe have nearly identical temperature and density despite appearing to be causally disconnected, having had no time to exchange information. Inflation solves this by suggesting that these regions were once much closer together before being rapidly expanded apart, allowing them to equilibrate in temperature and other properties. Another critical issue addressed by inflation is the flatness problem. This problem centers around the surprising fact that the universe appears spatially flat rather than curved. For the universe to appear as flat as it does today, its early density parameters must have been set with incredible precision. Inflation offers a solution by proposing that any initial curvature in the universe was diluted by the rapid expansion, causing the observable universe to appear flat on large scales. Furthermore, cosmic inflation provides an explanation for the origin of the large-scale structures we observe today, such as galaxies and galaxy clusters. Quantum fluctuations in the inflating universe were stretched to macroscopic scales and later became the seeds for these cosmic structures. These primordial fluctuations are imprinted in the cosmic microwave background as slight temperature variations, which we can observe today. Missions like the Planck satellite have mapped these tiny fluctuations with extraordinary precision, providing strong evidence for the inflationary model. The theory of cosmic inflation has become a cornerstone of modern cosmology, offering compelling explanations for the homogeneity, isotropy, and flatness of the universe, as well as accounting for the formation of the large-scale structures observed in the CMB. By explaining these phenomena, inflation provides critical insights into the universe's earliest moments and offers a coherent framework for understanding how the universe transitioned from an incredibly dense and small state to the vast structured cosmos we observe today. Central to the inflationary theory is the concept of the inflaton field, a hypothetical energy field that drove the rapid expansion of the universe. The inflaton field's potential energy dominated over other forms of energy, causing a repulsive gravitational effect that made space itself expand at an accelerating rate. This expansion was so rapid that the universe inflated by a factor of at least 10 to the 26 in less than a second. During this period, the energy density of the inflaton field remained nearly constant, allowing for the continued exponential growth of the universe. Following the end of inflation, the inflaton field decayed into particles and radiation, initiating the process known as reheating. This transition marks the beginning of the hot, dense state that characterizes the aftermath of the Big Bang. The rapid expansion driven by inflation had several far-reaching implications for the structure of the universe. For one, it smoothed out any initial irregularities, leading to the remarkably uniform and isotropic universe we observe today. Inflation also solved the horizon and flatness problems, providing a natural explanation for why distant regions of the universe share similar properties and why the universe appears geometrically flat. Moreover, inflation played a key role in the formation of the universe's large-scale structures. The quantum fluctuations in the inflaton field were magnified to cosmic scales during inflation, creating density variations that eventually grew into galaxies, clusters, and other cosmic structures. These fluctuations left their mark on the CMB as slight temperature variations, which have been mapped in detail by missions like the Planck satellite. Cosmic inflation is supported by multiple lines of compelling evidence, including the cosmic microwave background radiation, the remnant heat from the Big Bang, and the distribution of galaxies and galaxy clusters. The large-scale structure of the universe, which forms a vast cosmic web, is not random. Instead, it reveals the intricate patterns seeded by inflation, with filaments of galaxies connected by vast cosmic voids. This evidence continues to confirm that the theory of cosmic inflation provides a coherent, powerful explanation for the universe's early moments and its eventual large-scale structure. In summary, the study of the universe's origins has revealed an extraordinary tale of expansion, structure, and transformation. From the faint glow of the cosmic microwave background to the high-energy collisions at particle accelerators and the groundbreaking simulations on supercomputers, these scientific endeavors piece together a remarkable narrative of cosmic evolution. The theory of cosmic inflation stands at the heart of this narrative, offering a key to understanding the very foundations of the universe itself. The origins of the universe, once shrouded in mystery, can now be traced back to the earliest moments of cosmic history through the theory of inflation. This groundbreaking idea suggests that just after the Big Bang, the universe underwent an incredibly rapid expansion, stretching space-time by unimaginable amounts in a fraction of a second. This theory not only explains the distribution of galaxies and cosmic structures, but also resolves several long-standing issues in cosmology. Inflationary models, grounded in detailed computer simulations, closely replicate the large-scale structures we observe in the universe today. These simulations match the observations from telescopes and sky surveys, further solidifying inflation as a cornerstone of modern cosmology. One key piece of evidence for this theory comes from the flatness problem. According to Einstein's theory of general relativity, the universe must have a very specific density early in its history to maintain a flat geometry. Inflation solves this by stretching space so rapidly that any curvature is flattened, making the observable universe appear flat, regardless of its initial conditions. Another major puzzle that inflation helps to solve is the horizon problem. This issue arises from the fact that distant regions of the universe appear to share the same temperature, even though they should not have had any opportunity to exchange information due to the vast distances between them. Inflation explains this by suggesting that these regions were once in close proximity before being separated by the rapid expansion. This process allowed them to reach thermal equilibrium, resulting in the uniform temperature seen in the cosmic microwave background, CMB. The isotropy of the CMB, where its temperature remains consistent in all directions, points directly to inflation as the cause. Moreover, the detection of primordial gravitational waves could provide direct evidence of inflation. These waves are ripples in space-time created during the inflationary period and would leave an imprint on the CMB known as B-mode polarization. While initial claims of detecting these waves were later attributed to interstellar dust, the search continues. If confirmed, the discovery would offer compelling proof for the theory of inflation. All of these pieces of evidence, CMB and isotropies, large-scale structures, the flatness problem, and then the resolution of the horizon problem, build a robust case for inflation. Each of these findings aligns with predictions made by inflationary models, further cementing inflation as a vital element of our understanding of the cosmos. Before the advent of inflationary theory, questions about the universe's edge revolved around whether it was finite or infinite and what might lie beyond its observable limits. Inflation radically redefines these questions. During the inflationary period, the universe expanded exponentially, pushing regions that were once close together far beyond the observable horizon. This rapid expansion smoothed out any irregularities, creating a uniform, isotropic universe on large scales. As a result, the concept of an edge no longer applies in the traditional sense. Instead of a physical boundary, the edge is now understood as the limit of our observational capacity. The observable universe, which represents just a tiny fraction of the entire cosmos, might extend far beyond what we can currently detect. Inflation suggests that other regions beyond the observable universe could exist, possibly with different physical laws and constants. This leads to the theory of the multiverse, an ensemble of multiple, possibly infinite universes, each with its own unique properties. Each universe within the multiverse could have undergone its own inflationary period, resulting in vastly different laws of physics. Imagine a universe where gravity is stronger or where stars burn a different color. The possibilities are as endless as they are mind-boggling. The concept of the multiverse introduces an entirely new framework for understanding the universe. What was once thought to be a singular, isolated cosmos could instead be part of a vast, interconnected web of universes, each with its own distinct reality. This idea shifts our understanding of the universe's edge from a physical boundary to the limits of what we can observe. Inflation also redefines the universe's edge by expanding our concept of spacetime beyond the observable limits. It raises the possibility that the cosmos is far larger and possibly infinite than we ever imagined. As we continue to push the boundaries of observation, we may uncover new realms of reality, each with its own mysteries to explore. In this ever-expanding universe, inflation not only offers insight into the past, but also shapes our future understanding of the cosmos. The theory of inflation invites us to look beyond the observable, encouraging us to imagine a universe that stretches infinitely, full of possibilities that challenge our understanding of reality. This groundbreaking idea could still be unfolding, with new universes potentially emerging even now. The potential for discovery remains limitless. In this framework, pockets of space, inflating at varying rates, separate and become distinct universes, each encapsulated within its own bubble. The scientific foundation of this idea draws heavily from quantum field theory and general relativity. However, it's important to note that while the multiverse hypothesis is captivating, it remains speculative, as there is currently no direct observational evidence to support it. Yet, the mere concept of it is a tantalizing one, pushing the boundaries of what we understand about reality. It opens up endless questions about our place in a potentially infinite and ever-expanding cosmos. Imagine this. What if, in another universe, someone similar to you is contemplating the very same cosmic mysteries, but this time, under stars that glow in colors we've never even dreamed of? The observable universe is bounded by the distance light has traveled since the Big Bang, roughly 8 billion years ago. Beyond this horizon, what lies beyond remains an enigma that fuels deep, profound curiosity. Cosmologists often speculate that spacetime itself extends infinitely, stretching far beyond our visible universe. In these distant realms, there could be regions just like our own, complete with galaxies, stars, and planets. However, there's also the possibility that these distant areas may diverge from our universe in ways that are entirely beyond our comprehension. One intriguing theory suggests a vast, varied cosmic landscape where the fundamental laws of physics differ. This concept, known as cosmic variance, proposes that constants we consider universal, like the speed of light or the strength of gravity, could vary in regions far beyond our reach. Another possibility posits that beyond our observable universe lies an active cosmic inflationary field, a realm where rapid expansion continues, pushing the boundaries of space-time even further. This expansion extends the unseen frontier of the cosmos, one that challenges our understanding of the universe's true scale. While these theories stretch the imagination, they also underscore the inherent limitations that science faces. The speed of light and the finite age of the universe ensure that some mysteries may forever linger just beyond the reach of our telescopes. The observable universe, as we know it, is confined by the maximum distance from which light has had time to travel since the Big Bang, roughly 8 billion years ago. Light, despite its astounding speed of roughly 300,000 kilometers per second, has a finite reach. As the universe expands, this boundary, the observable universe, currently spans about 93 billion light years across, encompassing everything we can potentially see or detect. But the universe is not static. It's been expanding since its very inception. As it continues to grow, regions that were once close to us are now far beyond the reach of our observations. The light from these distant regions may never reach us because the space between us and them is stretching too rapidly. This accelerated expansion is driven by dark energy, a mysterious force that is pushing the universe apart. Even if we had the most advanced telescopes imaginable, the farthest objects would be receding from us faster than light can bridge the gap. This means no new light could ever reach us from these distant, effectively sealing off any hope of seeing beyond the cosmic horizon. This phenomenon creates a cosmological event horizon, an unknowable expanse beyond which lies a domain that time and space have sealed off. Our telescopes, though remarkable in their capabilities, are still bound by intrinsic and technical limitations. Instruments like the Hubble Space Telescope and the Very Large Telescope have offered unprecedented views of the universe, yet they are still hindered by atmospheric interference and the faintness of distant objects. As we stand at the edge of this vast cosmic frontier, we are left with more questions than answers. What exists beyond the observable universe? What other laws of physics govern these far-off realms? Can we ever truly grasp the full extent of existence, or are we forever destined to peer into the unknown, wondering what could be just beyond our reach? The universe, it seems, holds secrets that may forever remain out of sight, tantalizing and elusive, waiting to be discovered by future generations of explorers. The newest technological marvels, such as the James Webb Space Telescope, which operates in the infrared spectrum, are opening new frontiers in our understanding of the universe. Webb's ability to peer through cosmic dust and capture the early stages of galaxy formation is extraordinary. However, even with this cutting-edge technology, we are still limited by the light-blocking and distorting effects of interstellar and intergalactic media. Despite these obstacles, the future promises an even greater expansion of our observable universe, offering the potential to unveil realms and phenomena that are currently hidden from our view. One of the most exciting paths forward lies in the development of space-based telescopes, which eliminate the distorting effects of Earth's atmosphere. The upcoming launch of the Nancy Grace Roman Space Telescope, for example, aims to provide deeper and wider views of the cosmos than ever before. With its ability to capture vast swathes of sky across multiple wavelengths, it could unlock secrets about dark energy, galactic evolution, and even detect exoplanets with unprecedented clarity. But the advancements don't stop there. Proposed missions like the LUVOIR, Large Ultraviolet Optical Infrared Surveyor, would extend our reach even further, providing a giant leap in our ability to observe faint and distant objects, pushing the boundaries of our cosmic horizon. Beyond optical observations, gravitational wave observatories are opening a whole new way of probing the universe. Building on the pioneering work of LIGO and Virgo, these observatories detect the ripples in spacetime caused by cataclysmic events like black hole mergers. This innovative method allows scientists to study the universe in a way that is completely independent of electromagnetic radiation. Future space-based observatories, like the Laser Interferometer Space Antenna, LISA, will be able to listen for gravitational waves with even greater sensitivity, potentially unlocking details about the universe's early moments, long before the formation of the cosmic microwave background. In addition to these technological advancements, the future of astronomy will be significantly shaped by breakthroughs in computational power and artificial intelligence. As these technologies evolve, they will enable us to process and analyze the immense volumes of data these new instruments will generate. Artificial intelligence could help identify patterns and phenomena that were previously obscured by noise, offering insights into the very fabric of space-time and the universe itself. This new generation of observatories, combined with AI-driven analysis, could revolutionize our understanding of the cosmos, allowing us to explore mysteries that once seemed unfathomable. Studying the edge of the universe presents immense challenges, primarily due to the vast distances and the fundamental limitations imposed by the speed of light. When we observe distant celestial objects, we're also looking back in time, witnessing the state of these objects as they were billions of years ago. This temporal aspect complicates our understanding because we are piecing together a history that is always shifting. On top of these inherent observational limits, technological challenges continue to evolve. Even the most advanced telescopes are constrained by resolution and sensitivity. The faint light from the most distant objects is often overwhelmed by cosmic dust, intergalactic gas, and other obstacles that distort and attenuate the signals. Furthermore, our instruments are limited by their operational lifetimes, and maintaining their precision requires constant calibration to minimize errors and noise. Achieving the sensitivity needed to detect faint signals from the edge of the universe demands continuous advancements in detector technology, optics, and data processing algorithms. These advancements are both time-consuming and costly, yet absolutely necessary. Another major challenge is interpreting the data. Theoretical models of the universe often outpace our ability to empirically test them, meaning that much of our understanding of the universe's edge and beyond remains speculative. Complex phenomena like dark matter and dark energy continue to elude us, requiring novel approaches to both detect and understand their nature. The synthesis of observational data with theoretical models is an ongoing and iterative process filled with uncertainties. To tackle these challenges, we must embrace international collaboration, innovation, and a willingness to explore uncharted scientific territories. The next frontier in cosmology won't be reached with a single breakthrough. It will require not only technological innovations, but also a profound expansion of our theoretical frameworks. It's an exciting time for science, as the universe, with all its mysteries, lies just beyond the horizon, waiting for us to uncover its secrets. The concept of the multiverse theory is a fascinating and thought-provoking one, capturing the imagination of both scientists and philosophers alike. It suggests that our universe may not be the only one, but rather just one of potentially an infinite number of universes that form a grand, intricate multiverse. This idea, which challenges the very nature of reality, comes in several forms, each with its own explanation of how these multiple universes might originate and interact with each other. At the heart of one of the most famous multiverse theories lies the cosmological principle of cosmic inflation. In the moments immediately following the Big Bang, the universe is thought to have expanded at an astonishing rate, far faster than the speed of light. This rapid inflation could have caused bubble universes to emerge, each one evolving independently with its own unique set of physical laws and constants. The idea here is that these separate universes could exist alongside our own, each one following its own set of rules, forming a seemingly infinite network of parallel worlds. Another equally captivating concept arises from quantum mechanics and string theory. Quantum mechanics, which governs the behavior of particles at the smallest scales, introduces a bold interpretation known as the many worlds theory. According to this idea, every quantum event creates a new branch in the fabric of reality, resulting in the birth of a parallel universe where each possible outcome occurs. This branching process could create a vast, potentially infinite number of universes, each one representing a different version of reality. Meanwhile, string theory proposes the existence of multiple dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. These additional dimensions could be compactified, curled up so tightly that we cannot perceive them with our senses. In this scenario, different configurations of these compacted dimensions could lead to the creation of distinct universes, each with its own physical constants, rules, and properties. This concept suggests that the multiverse is not just a collection of universes, but a complex and dynamic landscape of realities with endless variations. However, despite the intellectual allure of these ideas, the multiverse theory remains highly speculative and controversial. The lack of direct observational evidence makes it difficult to test the existence of these alternate universes, and as a result, it is often met with skepticism. The theory pushes the boundaries of both scientific knowledge and philosophical inquiry, urging us to reconsider the very foundation of our understanding of reality. If the multiverse is indeed real, the implications would be profound, suggesting that our universe is just a tiny fragment of a vast, perhaps infinite, web of universes. This could redefine everything we know about existence, causality, and the nature of the cosmos itself. When it comes to the number of universes within the multiverse, the possibilities are as diverse as the theories themselves. Depending on the model you look at, the number of universes could range from a finite number to an infinite expanse of parallel worlds. In the context of cosmic inflation, the theory implies that the process of inflation could continue indefinitely, creating new universes ad infinitum. In this scenario, the number of universes would not be fixed, but would constantly grow as new bubbles of space-time form and evolve. Similarly, the many worlds interpretation of quantum mechanics suggests that every time a quantum decision is made, no matter how small, it creates a new branch in reality. This could theoretically lead to an astronomical number of universes, each one reflecting a different outcome of a quantum event. The complexity and sheer number of possible events would make it almost impossible to estimate the total number of universes created by this process, but it could very well be infinite. String theory offers yet another possibility through its landscape theory, which suggests that the number of potential universes could be even more staggering. The theory proposes that there are a vast number of ways the additional dimensions could be compactified, each configuration resulting in a different universe with its own set of physical constants and laws. This means that the multiverse could contain a nearly unimaginable number of possible universes, each one distinct from the others in ways we can't even begin to comprehend. Despite the allure of these possibilities, the lack of empirical evidence makes it difficult, if not impossible, to verify these theories with current technology. While there are promising mathematical frameworks supporting the existence of a multiverse, the challenge of obtaining direct evidence for the existence of these parallel universes remains a monumental task. As a result, the multiverse theory, though captivating, remains a speculative frontier in the realms of both science and philosophy, encouraging us to expand our thinking and question the very nature of reality itself. As we venture deeper into the mysteries of the cosmos, one question persists, growing ever more profound. Are we alone in the vastness of space, or do countless other universes exist, each with its own set of laws and realities? To begin addressing such a question, advanced observational techniques, cutting-edge instruments, and groundbreaking theoretical breakthroughs will be absolutely essential. Without these, even the most basic exploration of the multiverse remains far beyond our reach. But the mere possibility of an infinite number of universes challenges our very conception of reality. An idea that not only humbles us, but also exhilarates the imagination. Theories surrounding the multiverse are as diverse as the scientific frameworks that support them. Each theory proposes different mechanisms by which multiple universes might exist, expanding our understanding of reality in ways once deemed unthinkable. Broadly speaking, these theories can be grouped into several categories, each emerging from distinct scientific principles and theoretical frameworks. One of the most captivating and widely discussed is the cosmological multiverse, an idea born from the theory of cosmic inflation. This concept suggests that shortly after the Big Bang, during the rapid and dramatic expansion of space, our universe may have been just one of many bubbles created. These bubbles, each representing a distinct universe, would have their own separate physical laws, constants, and characteristics. What's even more fascinating is the possibility that these universes are physically separated from each other by vast regions of inflating space, regions beyond our observational reach, leaving us with a tantalizing hint of an infinite cosmos yet to be explored. Then there is the quantum multiverse, a theory rooted in the many worlds interpretation of quantum mechanics. This perspective suggests that every quantum event, which could have multiple outcomes, leads to the branching of universes, each one unfolding according to a different possibility. The results? A sprawling, ever-growing tree of universes, each one slightly different, each one parallel to our own, based on the choices made at the quantum level. If this theory holds any merit, it implies that every tiny decision and every fluctuation in the quantum realm has given rise to its own universe, a staggering number of potential realities. The brain multiverse takes a different approach, emerging from string theory. According to this theory, what we perceive as our universe may simply be a three-dimensional brain, short for membrane, floating within a higher dimensional space. This higher dimensional space could harbor other brains, each potentially governed by different laws of physics. The idea that our universe might just be one of many such brains opens up the possibility of inter-brain collisions, which could have profound and observable effects on our universe, possibly even explaining major events like the Big Bang itself. The brain multiverse offers an exciting and somewhat unsettling new perspective on the nature of existence. Another intriguing version is the landscape multiverse theory, also rooted in string theory. In this model, the cosmos is made up of a vast landscape of possible vacuum states, each one representing a different universe. Each of these states comes with its own unique laws of nature, constants, and forms of physical reality. Our universe, in this view, is just one small section of this vast, almost infinite landscape. This theory is particularly compelling because it might explain why the laws of physics in our universe seem so finely tuned for life. What we observe as the constants of nature could simply be one of many possible configurations, realized out of a multitude of potential outcomes. Lastly, There's the cyclic multiverse, which proposes that the universe undergoes an eternal cycle of creation and destruction, marked by repeated big bangs and big crunches. In this view, each cycle gives birth to a new universe, one that may differ significantly in its physical laws and initial conditions. These cycles would effectively produce a sequence of distinct, ever-evolving universes, each one slightly different from the last, offering an endless variety of possibilities. These varying multiverse theories, while speculative, push the boundaries of our understanding of the cosmos. They challenge us to think beyond the limits of what we can observe and consider the profound complexities and potentials that might lie just beyond our observational horizon. Each type of multiverse theory offers a unique lens through which to explore the ultimate nature of reality. In doing so, they raise questions that could fundamentally alter our understanding of existence itself, suggesting a much broader and more intricate cosmos than we ever imagined. Currently, we have yet to uncover direct evidence for the existence of a multiverse. However, a wealth of indirect clues and theoretical frameworks provide compelling reasons to take the multiverse hypothesis seriously. One of the most persuasive pieces of evidence comes from cosmic inflation theory. This theory explains the rapid expansion of the universe in the moments following the Big Bang and predicts that this inflation could have given rise to multiple causally disconnected regions, what we might think of as bubble universes. Some variations of this theory even suggest that these bubbles form in an ongoing eternal process, constantly spawning new universes. Supporting this notion, observational data from the cosmic microwave background radiation, the afterglow of the Big Bang, suggests a remarkable uniformity and flatness across the universe. This is a key prediction of cosmic inflation and adds weight to the idea that inflation might have created multiple universes, though it doesn't directly prove their existence. The more we learn about inflation, the more plausible the multiverse becomes as a framework within which to understand the evolution of the cosmos. The intriguing idea of a multiverse, or a collection of parallel universes, continues to captivate the imagination of physicists and the general public alike. While still primarily speculative, various lines of indirect support from quantum mechanics, cosmology, and theoretical physics lend some weight to the possibility of multiple universes existing beyond our own. One such concept comes from quantum mechanics, specifically the many worlds interpretation, MWI. This theory offers a fascinating approach to solving the quantum measurement problem. Rather than collapsing to a single outcome, MWI proposes that every possible result of a quantum measurement actually occurs, each in its own separate, branching universe. Though this remains highly theoretical and is not yet supported by experimental evidence, it aligns with the mathematical framework of quantum mechanics and has found an increasing number of supporters within the physics community. Another significant contribution to the multiverse discussion is the anthropic principle. This principle observes that the physical constants of our universe appear to be finely tuned to allow for life as we know it. In a vast or even infinite multiverse, where different universes might have different constants, the anthropic principle suggests that we might find ourselves in a rare universe where the conditions are just right for life to exist. While not providing direct evidence of other universes, it offers a compelling reason for why our universe appears to be so remarkably suited for life. This idea suggests that we are not living in an exceptional universe, but rather one among many where the conditions just happen to align perfectly for the emergence of life. String theory, one of the most promising frameworks in theoretical physics, also offers a compelling multiverse model. String theory posits the existence of a landscape of possible vacua, each corresponding to a different set of physical laws and constants. This idea suggests that our universe is just one of a near infinite number of possible vacuum states. As string theory strives to be a unified theory of everything, it contends that the existence of a single, unique universe may not be the most natural or inevitable outcome. Instead, the landscape multiverse theory envisions countless universes, each with its own distinct set of physical laws. While these ideas provide tantalizing possibilities, they still fall short of offering conclusive proof. The challenge lies in the fact that these theories are, at this point, beyond the reach of current experimental validation. Despite the theoretical allure of these multiverse models, the question of whether we are part of a grand interconnected web of universes remains unresolved. The potential interactions between universes within a multiverse are a particularly fascinating subject of study, with theories diverging on the nature and possibility of such interactions. In most models, universes are considered causally disconnected, meaning they do not influence one another in any observable way. However, some speculative theories propose that there might be a mechanism through which universes could interact, even if these interactions are indirect or minimal. One of the more intriguing possibilities arises from the cosmological multiverse model, which is often linked to cosmic inflation. In this scenario, the universe undergoes rapid expansion in its early moments, leading to the formation of bubble universes, each expanding within its own region of space. These bubble universes are separated by regions of inflating space, making direct interaction virtually impossible. However, some theories suggest that if two such bubble universes were to collide, they could leave detectable imprints on the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. These imprints might appear as anomalies or unusual patterns in the CMB data, which could potentially provide indirect evidence for such collisions. Though this remains purely hypothetical, the idea has captured the attention of researchers, and future observational advancements could one day test its validity. In the quantum multiverse scenario, which stems from the many worlds interpretation, each universe represents a different branch created by the infinite possibilities that arise from quantum events. These branches are non-interacting by nature, each evolving independently with its own timeline and set of events. There is currently no theoretical framework supporting any interaction between these parallel universes, as they are considered to be completely separate entities within their own distinct realities. Thus, while the many worlds interpretation proposes a vast network of parallel universes, it does not suggest that these universes have any form of observable or measurable influence on each other. Although the evidence for the multiverse remains indirect and speculative, the discussion is far from over. Theoretical frameworks such as quantum mechanics, string theory, and cosmological models continue to evolve and provide new insights into the nature of reality. For now, we are left to wonder whether we truly live in a unique, singular universe, or if we are part of an expansive, interconnected multiverse, where countless other universes might coexist, each with its own rules and realities. The tantalizing question of our place in this grand cosmic tapestry remains one of the most profound mysteries of modern physics. Only through future advancements in both theoretical understanding and observational techniques will we come closer to uncovering the truth behind the existence of the multiverse. The brain. The concept of the multiverse inspired by string theory brings forward a compelling and mind-bending possibility. What if our universe is nothing more than a three-dimensional brain floating in a higher dimensional bulk? This remarkable idea suggests that other brains could exist in parallel to ours, each contained within this vast multidimensional space. Imagine this: different universes, each with distinct properties, cohabiting the same cosmic neighborhood and potentially interacting with one another in ways we can barely fathom. Now, in some models, these interactions between brains are not just theoretical, but could actually be possible. Picture this: colossal cosmic collisions between these brains. These events, some speculators propose, could account for the creation of new universes or even explain certain high-energy phenomena that baffle scientists today. Could the Big Bang itself have been the result of a cataclysmic collision between two such brains? The implications are staggering. Yet, despite its mind-blowing potential, this idea remains purely speculative, far beyond the capabilities of current experimental verification. But what about quantum entanglement across universes? This is where things get even more fascinating. Imagine quantum particles maintaining their entangled state across different branches of the many worlds multiverse. Could the connections between these particles persist beyond the boundaries of individual universes? Could there be subtle correlations, distant echoes of one universe influencing another? The idea is nothing short of extraordinary, yet it remains, for now, largely untested and speculative. Most models of the multiverse, while offering hints of potential interaction, propose that universes evolve independently, isolated in their respective dimensions. The idea of interaction, whether direct or indirect, would require groundbreaking advances in both theoretical physics and observational technology to even consider proving its existence. Until those leaps occur, the notion of inter-universe communication remains a tantalizing mystery, one that continues to stir the imagination of physicists and cosmologists alike. At the heart of this theory is brain cosmology, a fascinating concept within string theory and its more expansive cousin, M-theory. Brain cosmology suggests that our familiar four-dimensional universe, 3 spatial dimensions plus time, might be nothing more than a 3-dimensional brain floating within a higher dimensional space, often referred to as the bulk. This bulk, containing extra dimensions that are typically hidden from our perception, could house multiple other brains, each with its own set of physical laws and properties. What's most captivating about brain cosmology is the role gravity plays in this expansive theory. Unlike the electromagnetic forces which are confined to the brain, gravity is unique in that it can leak into the bulk, explaining why it is so weak compared to the other fundamental forces of nature. It essentially diffuses its power across multiple dimensions, making it incredibly difficult to observe on a large scale. In this higher dimensional universe, one of the most thrilling concepts proposed is that of brain collisions. These cataclysmic events could result in dramatic outcomes, perhaps even the birth of new universes. Imagine this: the cyclical expansion and contraction of the universe, driven by periodic collisions between brains. Each collision could reset the cosmic clock, sparking a new Big Bang and marking the beginning of another universe. This cyclical model, sometimes referred to as eternal inflation, proposes that the universe undergoes infinite cycles of expansion and contraction. With each cycle, a new universe is born, with the previous one collapsing in on itself in a big crunch. While these ideas are breathtaking and provide profound insight into the nature of the cosmos, they also present immense challenges. Testing these concepts directly is beyond our current technological and observational capabilities. But that doesn't diminish their allure. Brain cosmology, with its radical new perspectives, offers an exciting framework for understanding the universe, encouraging us to think beyond the limits of our own experience. The question of whether universes could collide, interact, or even communicate remains one of the most fascinating, open-ended puzzles in modern cosmology. Indeed, the exploration of brain cosmology continues to expand the frontiers of theoretical physics. With each new idea, we edge closer to understanding our place in the vastness of the cosmos, and perhaps one day the secrets of the multiverse itself. Until then, the study of these higher dimensional realms remains a deeply captivating and profound journey into the unknown. However, there are tantalizing implications that might be observable or inferred through indirect means. For instance, some cosmological models predict that brain collisions could leave imprints in the cosmic microwave background or influence the distribution of galaxies and large-scale structures in the universe. Another potential area of exploration lies in detecting higher dimensional gravitational waves, which could reveal new information about the bulk space and the interactions between brains. While brain cosmology remains a highly speculative and mathematically complex field, it offers profound insights and challenges our understanding of space, time, and the very nature of the universe. It extends the boundaries of conventional cosmology, opening new realms of inquiry that could fundamentally alter our perception of reality and our place within the cosmos. The concept of brains is central to string theory and its extension, M-theory, which reshapes our understanding of higher dimensional space. Within these theories, brains, short for membranes, are multidimensional objects that can extend across various spatial dimensions. For instance, a one-dimensional brain is a string, a two-dimensional brain is a membrane, and a three-dimensional brain is often referred to as a three-brain, which is one way some theorists describe our universe. These brains exist within a higher dimensional space known as the bulk, which can have numerous dimensions beyond the familiar 3 spatial and 1 temporal dimension that we experience daily. According to string theory, our entire universe could be viewed as a 3-dimensional brain floating within this higher dimensional bulk. One of the intriguing aspects of brain theory is how it addresses the hierarchy problem in physics, specifically why gravity is so much weaker compared to other fundamental forces like electromagnetism and the strong force. Brain cosmology suggests that while other forces are confined to the brain, gravity can propagate through the bulk. This leakage into higher dimensions might explain why we perceive gravity as weak, as it is being diluted across multiple dimensions beyond our observable universe. The higher dimensional space of the bulk also suggests the existence of multiple brains, potentially leading to multiple universes, each with distinct physical laws and constants. Brain collisions and interactions within this multidimensional space could produce phenomena observable in our universe. One hypothesis even suggests that the Big Bang could have resulted from the collision of our three-brain with another brain within the bulk. Such an event would inject immense energy into our brain, initiating conditions favorable for the Big Bang. Another fascinating implication of brain theory and higher dimensional space is the potential to detect phenomena arising from these extra dimensions. This might include identifying gravitational waves that originate from interactions within the bulk, or observing imprints in the cosmic microwave background that hint at a deeper structure to spacetime. Advanced theoretical and experimental work, such as probing for microscopic black holes or exploring large-scale cosmic structures, could eventually offer empirical clues about the higher dimensional brain landscape. Brains are multi-dimensional entities embedded within a higher dimensional bulk, providing a framework that expands our understanding of space-time and gravity. They bridge familiar physical laws with the exotic possibilities of dimensions beyond our perception, unlocking a world of scientific inquiry that pushes the boundaries of modern cosmology and theoretical physics. Direct evidence for brain cosmology, like much of modern theoretical physics, remains elusive due to the extreme difficulty in testing phenomena occurring at energy scales or dimensions far beyond current experimental capabilities. However, several indirect lines of evidence and theoretical motivations support the viability of brain cosmology as a compelling framework. One key area of indirect support comes from the consistency of brain cosmology within the broader context of string theory and M theory. These frameworks aim to unify the fundamental forces of nature, including gravity, within a higher dimensional setting. String theory, which posits that particles are actually tiny vibrating strings, naturally includes multidimensional brains as part of its mathematical structure. Brain cosmology helps address some perplexing issues in physics, such as the hierarchy problem, the puzzling question of why gravity is so much weaker than other fundamental forces. By proposing that gravity leaks into extra dimensions, brain cosmology offers a plausible explanation for this discrepancy. Additionally, brain cosmology provides insight into the initial conditions of the universe, shedding light on the origins and structure of everything we observe. In the realm of theoretical cosmology, certain models, such as the cyclic or ekpyrotic universe theories, provide an intriguing framework that challenges our traditional understanding of the cosmos. These models suggest that catastrophic events like the Big Bang may not be isolated incidents, but rather the results of collisions between brains, multidimensional objects that exist within a higher dimensional space. Such interactions have the potential to explain many of the universe's most puzzling features. One of the striking aspects of brain cosmology is its ability to account for the homogeneous and isotropic nature of the cosmic microwave background, CMB radiation, the faint glow that pervades the entire universe, and the large-scale distribution of structures like galaxies and clusters. These features are often seen as remnants of the early universe, but in the context of brain models, they might also be the result of past brain collisions, energy-rich events that reshape the cosmos. While current cosmological observations don't directly confirm the existence of brains or higher dimensions, they have provided subtle hints that could point toward their reality. One such anomaly lies within the CMB, where unexpected temperature fluctuations and peculiar alignments in the radiation could be interpreted as signatures of brain interactions or higher dimensional processes. These anomalies, although not definitive, offer tantalizing clues that suggest our universe might be the product of forces beyond the familiar three dimensions. Furthermore, the search for gravitational waves has opened a new frontier in astrophysics, one that might eventually detect waves originating from dimensions far beyond our observable universe. If these waves were detected, it could offer the first real evidence of higher dimensional phenomena. Similarly, particle physics experiments, such as those conducted at the Large Hadron Collider, could provide indirect clues. Imagine discovering particles that behave in ways consistent with the existence of extra dimensions, or observing high-energy phenomena that suggest interactions beyond the standard model. Such discoveries would not only bolster the case for brain cosmology, but fundamentally alter our understanding of the universe's workings. The possibility of microscopic black holes or particles exhibiting characteristics predicted by string theory would further validate brain models. These breakthroughs would not just be theoretical victories, they would offer tangible evidence that our universe is far more complex and interconnected than we ever imagined. While direct evidence for brain cosmology remains elusive, the indirect support from various experimental and theoretical avenues is compelling, suggesting that our universe may be part of a vast, higher dimensional reality yet to be fully understood. The collision of brains, as proposed by models like the ekpyrotic universe theory, presents a fascinating explanation for the origin of the universe. In this framework, our observable universe is envisioned as a three-dimensional membrane, or three-brain, existing within a higher dimensional space known as the bulk. Within this bulk, other brains, each with its own unique set of physical properties, exist in parallel with our own. The intriguing aspect of this theory is that these brains are not static. They move and fluctuate within the bulk, and when two brains approach each other closely enough, a collision can occur. Such a collision could be an incredibly energetic event, one that releases a colossal amount of energy, resetting the conditions of the universe. In the ekpyrotic model, this collision is proposed as an alternative to the traditional Big Bang theory. Instead of a singular explosion marking the birth of the universe, the collision of brains releases an enormous amount of energy, igniting a period of rapid expansion similar to the inflationary phase in conventional cosmology. This event would set the initial conditions required for the formation of a new universe, creating the right environment for matter, galaxies, and other cosmic structures to emerge. The energy released during the collision would serve as the catalyst for a Big Bang, producing radiation, particles, and forces that eventually give rise to the cosmos as we know it. In this theoretical framework, the universe we observe today could be the product of an ongoing cycle of brain collisions, each collision resetting the conditions and setting the stage for a new universe. While much of this remains speculative, the allure of brain cosmology lies in its potential to unify disparate aspects of physics, from cosmology and particle physics to string theory and beyond. With continued advancements in experimental techniques and theoretical models, we may one day discover empirical evidence that supports this fascinating and bold vision of our universe's origins. The idea that our universe is the result of a cosmic collision between higher dimensional brains is both exhilarating and deeply humbling. It challenges our understanding of reality and pushes the boundaries of human knowledge. The quest for answers to these profound questions may one day lead to a paradigm shift in cosmology, changing the way we view the universe and our place within it. One of the most captivating aspects of the eroctic model is its potential to shed light on several of the universe's most perplexing features. For instance, the uniformity and isotropy we observe in the cosmic microwave background radiation could be the natural result of a brain collision. This model may also offer insightful explanations for the large-scale structures in the cosmos and certain facets of cosmic evolution that the traditional Big Bang theory struggles to explain. While directly detecting a brain collision remains a monumental challenge, indirect evidence could point toward its validity. Certain patterns and anomalies within the CMB might hint at the remnants of such a collision, suggesting a connection between this phenomenon and the observable universe. Additionally, gravitational waves from high-energy events within higher dimensional space could serve as crucial evidence supporting the brain collision hypothesis, opening up entirely new avenues for scientific exploration. The idea of brains colliding to generate new universes is nothing short of revolutionary. It presents a bold new perspective on the origins of our cosmos, one that is deeply theoretical and difficult to directly test. But this model gives rise to fresh and exciting possibilities for understanding the fundamental forces shaping reality, especially the cosmic processes that govern the birth and evolution of universes. As our observational and experimental techniques continue to improve, we may come ever closer to uncovering the mysteries of brain cosmology and the true nature of our universe's origins. Now, diving deeper into the realm of brain cosmology, the eroctic model provides a mind-bending alternative to the Big Bang theory. The name eroctic is derived from the Greek word for conflagration, which encapsulates the essence of this theory. The idea that our universe was born not from an explosive singularity, but from a cosmic collision within a higher dimensional space. Imagine, if you will, a boundless multidimensional universe where three-dimensional reality is but one of many floating brains, suspended in an enormous expanse. These brains occasionally make contact, and it is this very collision that the eroctic model suggests sparked the birth of our universe. This conceptual framework, though complex, offers a remarkable insight into the early stages of the cosmos. The energy released during a brain collision is thought to have triggered the hot, dense, and rapidly expanding state that we associate with the Big Bang. The model holds significant promise for explaining some of the most enduring mysteries in cosmology, such as the uniformity observed in the cosmic microwave background radiation and the formation of the universe's large-scale structure. By incorporating principles from string theory and higher dimensional space, the eroctic model attempts to provide a more holistic understanding of the origins of the universe, urging us to look beyond conventional boundaries and consider the complex interplay of brains that could underlie the very fabric of the cosmos. Furthermore, one of the most tantalizing ideas that emerges from this domain is the holographic principle, a concept that challenges our fundamental understanding of space and information. Initially proposed by physicist Gerard 't Hooft and later expanded by Leonard Susskind, this principle suggests that the entire informational content of a three-dimensional space could be encoded on a two-dimensional boundary. In simpler terms, just as a hologram on a flat surface can generate a three-dimensional illusion, our universe might itself be a projection of information stored on a distant cosmological boundary. To visualize this, imagine stepping into a room where every object, the furniture, the people, everything, appears to be three-dimensional, but is actually a projection from a two-dimensional surface. This is similar to what the holographic principle proposes about the universe. One of the most striking applications of this theory can be seen in black holes. According to the laws of thermodynamics combined with Einstein's theory of relativity, any information about objects that fall into a black hole isn't lost. Instead, it's encoded on the event horizon, the black hole's boundary. Extending this notion to the cosmos suggests that all the information within our vast universe, seemingly infinite, may in fact be encoded on a distant two-dimensional surface. As we explore these revolutionary ideas, we begin to realize that we may be on the cusp of a deeper understanding of the universe, one that challenges everything we know about space, time, and reality itself. Whether the brain collision model or the holographic principle holds the key to the true origins of the universe, they both push us to rethink our place in the cosmos and the very nature of existence. As our tools and techniques evolve, so too may our grasp of these fascinating theories, which could eventually lead us to answer some of the most profound questions about our universe. This revolutionary principle reshapes our understanding of dimensions and the very nature of reality itself. It bridges the gap between the vast cosmic scales of galaxies and stars and the minuscule quantum phenomena that govern the behavior of subatomic particles. The notion that our universe might be a hologram has been gaining serious attention, with the holographic principle suggesting a complex relationship between space, information, and dimensionality. Imagine, for a moment, a three-dimensional image generated by light waves on a two-dimensional surface. This is a hologram, where depth and reality seem to emerge from a flat plane. Now, apply that concept to the cosmos. The idea here is nothing short of extraordinary. The entire volume of our universe, filled with galaxies, stars, and cosmic dust, could be an immense three-dimensional image of data. Information that can be fully described by data located on a two-dimensional surface. Just like a hologram projects depth from a flat plane, could the cosmos itself be projected from something equally flat and distant? This is not the stuff of science fiction, but a theory deeply rooted in the realms of theoretical physics, particularly in the study of string theory and black holes. The concept gains weight when we consider black holes, those mysterious cosmic entities with gravitational pulls so powerful that not even light can escape. The physics of black holes has led to a profound realization. The information about anything falling into a black hole is not lost. Instead, it is stored on the event horizon, the two-dimensional surface surrounding the black hole. This key insight opened the door to a fascinating question. If the volume of a black hole can be described by information on its surface, could the entire universe operate under similar principles? The idea that the universe might be a projection from a distant two-dimensional surface begins to seem less far-fetched. Moreover, physicists have uncovered intriguing mathematical congruencies between theories describing phenomena in higher dimensional spaces and those at their boundaries. These congruencies provide further support for the holographic perspective. These revelations invite us to reconsider everything we know about space and reality. What if our multidimensional universe, rich in complexity and depth, is in reality just the grandest of cosmic illusions, projected from a far-off surface in the cosmos? The exploration of the holographic principle, though deeply theoretical, is supported by several compelling strands of evidence that resonate with the fundamental laws of physics and cosmology. One of the most convincing pieces of evidence comes from the study of black holes. Entropy, which measures the amount of disorder or information in a system, behaves in an unexpected way when it comes to black holes. In a groundbreaking discovery, physicists Jacob Bekenstein and Stephen Hawking found that the entropy of a black hole is not proportional to its volume, as one might expect. Instead, it is proportional to the area of its event horizon, the two-dimensional boundary surrounding the black hole. This astonishing discovery suggests that all the information within the black hole could be encoded on its surface, directly pointing to the holographic nature of the information. Another powerful strand of evidence emerges from the realm of string theory, particularly the concept known as the ADS-SCFT correspondence. This theoretical framework, proposed by Juan Maldacena, establishes a duality between a gravity theory in a higher dimensional anti-de Sitter ADS space and a quantum field theory on its lower dimensional boundary. Essentially, this duality shows that a three-dimensional gravitational theory can be fully described by a two-dimensional quantum field theory. This connection encapsulates the essence of the holographic principle and strengthens the notion that our universe, with its gravity and dimensions, could indeed be a holographic projection from a more fundamental, lower dimensional reality, one without gravity. These theoretical breakthroughs do more than lend credence to the holographic principle. They open new pathways in our quest to understand quantum gravity and the very fabric of the cosmos. They invite us to explore deeper into the nature of reality, pushing the boundaries of what we consider possible. Yet, while these ideas are profound and captivating, empirical validation remains an ongoing challenge, and the true nature of our universe continues to elude full understanding. But one thing is certain: the holographic principle has ignited a new era of thought in physics, offering a tantalizing glimpse into the possibility that reality, as we know it, may not be as it seems. The holographic principle stands as one of the most captivating and transformative ideas in modern cosmology. It reshapes our understanding of reality, challenging deeply held assumptions about the fabric of the universe. At its core, this principle suggests that the three-dimensional world we experience might not be as it seems. Instead, it could be a projection of information encoded on a two-dimensional boundary. This concept forces us to rethink the very nature of space, time, and existence, offering a radically new perspective on the cosmos. Traditionally, we perceive the universe as a vast, three-dimensional expanse where objects exist within definite volumes of space. Yet, the holographic principle flips this notion on its head. It proposes that our three-dimensional reality, with all its intricate complexities, could merely be a projection of data mapped onto a distant, two-dimensional surface. The idea that the universe we see could be nothing more than a cosmic illusion has profound implications. Not only does it challenge our understanding of dimensions, but it also forces us to reconsider the fundamental nature of matter and its properties. What does it mean for something to exist if it's simply a holographic projection? One of the most intriguing aspects of the holographic principle is its potential to reconcile two seemingly incompatible pillars of modern physics: quantum mechanics and general relativity. For decades, these theories have stood as the foundational frameworks of physics, yet they have resisted any attempt at a unified theory. Quantum mechanics offers an excellent explanation of the behavior of subatomic particles, while general relativity explains the workings of gravity and the motion of celestial bodies. However, the challenge lies in merging these two frameworks into a single, cohesive theory of the universe. The holographic principle provides a tantalizing solution by suggesting that the complexity of our three-dimensional world, with all its intricate quantum interactions, can be encoded on a simpler, lower-dimensional surface. This insight opens up new possibilities for a unified theory of quantum gravity, a breakthrough that could reshape our entire understanding of the cosmos. Moreover, the holographic principle radically shifts our understanding of information in the universe. In this new paradigm, information becomes more fundamental than the space in which it resides. Rather than viewing the universe as a collection of particles occupying space, we are invited to imagine a universe built from bits of information etched onto a cosmic surface. This concept transforms the way we think about reality. It implies that our universe might not be an intrinsic physical reality at all, but an emergent phenomenon arising from a deeper, underlying informational structure. The shift from a material to an informational worldview has profound philosophical and scientific ramifications, suggesting that reality itself could be far more fluid and interconnected than we ever imagined. As we delve deeper into the holographic principle, its potential to revolutionize both science and philosophy becomes clearer. It offers new insights into the very nature of existence, urging us to reconsider the limits of our perception and the boundaries of the known universe. One of the most intriguing consequences of this principle lies in its implications for the edge of the universe. Traditionally, we think of the universe's boundary as a mere spatial limit, a frontier beyond which nothing exists. However, the holographic principle suggests that this boundary could be far more significant. It might not just mark the edge of the cosmos, but could serve as a two-dimensional surface containing all the information about the entire three-dimensional universe. This means that every particle, every event, and every interaction within the universe could be described by information inscribed on this boundary. The edge is no longer a passive limit. It is an active participant in the dynamics of the universe itself. This rethinking of the universe's boundary has profound implications for our understanding of information and entropy. If all the information about the universe is stored on a two-dimensional surface, then what happens within the volume of the universe is deeply connected to processes occurring at this edge. The boundary is no longer just a static feature, but a dynamic and active force in shaping the events within the universe. This new perspective not only challenges conventional ideas about space and time, but also opens the door to groundbreaking insights into the true nature of the universe. Could the entire cosmos, with all its complexity, be encoded on a two-dimensional surface? The holographic principle pushes us to think beyond the limits of our traditional understanding, inviting us to explore the profound mysteries of the universe in ways we never thought possible. The concept that the universe may not simply be defined by its vast internal volume challenges the very core of our understanding of cosmology. Traditionally, we have focused on the substance within the cosmos: stars, galaxies, dark matter. But this perspective shifts the conversation toward something far more abstract, yet equally crucial: the boundaries and edges of the universe. No longer can we ignore the role that these limits play in shaping the nature of existence itself. The holographic principle, a groundbreaking idea in theoretical physics, tells us that everything we perceive within the universe, from distant stars to the smallest quantum particles, could be encoded on a distant boundary. A boundary that's not just a physical frontier, but an essential feature of the cosmos's very construction. This paradigm shatters our conventional views of locality. In classical physics, we assume that an object's properties, like its mass or energy, are localized within the space it occupies. But if the universe is indeed a hologram, the interactions and properties of objects may actually be projected from this distant boundary, implying that what we observe locally is merely a shadow of a more profound, interconnected reality. The implications of this could alter everything we know about black holes, quantum entanglement, and even our potential to harness quantum information for revolutionary technologies. The holographic principle is not just a concept, it is a challenge to our very understanding of space, time, and the universe as a whole. Now, let's turn our attention to one of the most mysterious phenomena in the universe: black holes. These celestial objects embody some of the most extreme conditions in nature. The sheer gravitational forces they exert are so intense that they warp the fabric of space-time itself. According to Einstein's general theory of relativity, black holes form when a massive star exhausts its nuclear fuel and collapses under its own gravity, creating a singularity, a point of infinite density where the known laws of physics break down. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. It's this lack of light emission that renders black holes invisible, making them a cosmic enigma. The event horizon acts as a one-way membrane where anything crossing it becomes irreversibly drawn toward the singularity, contributing its mass and information to the black hole. Despite their ominous reputation as cosmic vacuum cleaners, black holes are far from mere destructive forces. They are, in fact, essential players in the formation and evolution of galaxies. Supermassive black holes, which can weigh millions or even billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. Their immense gravitational influence plays a crucial role in shaping the dynamics of their host galaxies, often controlling their growth, star formation, and even their shape. Moreover, black holes are not just astrophysical curiosities. They are fundamental to probing the deepest questions at the crossroads of quantum mechanics, general relativity, and information theory. Perhaps the most intriguing insight into black holes comes from the work of Stephen Hawking, whose theory of Hawking radiation suggests that black holes could slowly evaporate over time. According to this theory, quantum effects near the event horizon allow black holes to emit radiation, a process that implies they are not eternal. This revelation introduces profound questions about the nature of information. What happens to the information contained within a black hole? Is it lost forever, or does it somehow escape? This puzzle has generated a wealth of scientific debate and remains an open question in modern physics. Black holes, therefore, serve as natural laboratories for testing the limits of our understanding and pushing the boundaries of scientific inquiry. The connection between black holes and the edge of the universe is far from coincidental. Through the holographic principle, black holes offer a unique lens through which we can reconsider the very nature of cosmic boundaries. While black holes may not represent the literal edge of the universe, they serve as a model for how boundaries and information might work on a cosmic scale. The idea that all the information about an object that falls into a black hole is encoded on its event horizon, its two-dimensional boundary, mirrors the holographic theory that all the information in the universe could be stored on a distant cosmological boundary. In this view, the entire universe, from galaxies to quantum particles, could be understood as a projection from a distant boundary. This insight has profound implications for how we think about space and time. If black holes can encode all the information of the matter within them on their event horizons, then perhaps the entire universe functions in a similar manner. The edge of the universe may not simply be a spatial boundary, but rather an informational one, a place where the laws of physics could change. In this way, black holes offer us a glimpse into the fundamental principles that govern not only the forces of nature, but the very structure of reality itself. They are, in a sense, the cosmic mirrors reflecting the deepest truths about the universe, urging us to rethink the very nature of existence and the boundaries of knowledge. In this context, the edge of the universe is not merely an outermost spatial frontier, but rather a deep conceptual boundary, a kind of surface inscribed with all the information of the cosmos. As we venture into the mysteries of black hole thermodynamics and Hawking radiation, our understanding expands. The suggestion that information trapped within black holes could eventually escape, radiated back into the universe, opens intriguing possibilities for cosmic-scale information retrieval. Could it be that the entire history of our universe, along with its contents, is retrievable from a distant, encircling boundary? This concept challenges the conventional limits of space and time, offering profound insights into how cosmic information might be stored and transferred. Black holes, long regarded as the enigmatic cosmic giants, hold crucial clues to how the universe's information might be encoded and disseminated. The edge of the universe then becomes not a spatial limit, but a fundamental feature of its informational structure. It reframes our understanding not as a boundary defined by distance, but as a surface shaped by the flow and retention of information. In essence, black holes become critical windows, portals, into a deeper cosmic narrative that challenges our perception of reality, where space, time, and information are intricately intertwined. The concept of a singularity, integral to both astrophysics and general relativity, further complicates our understanding. A singularity is a point in space where the density of matter and the gravitational field become so extreme that the laws of physics, as we know them, break down. It represents an area where matter is compressed to an infinitely small volume, resulting in infinite curvature of space-time. The most prominent example of this phenomenon is the singularity at the heart of a black hole, where the core of a massive star collapses under the relentless force of gravity, crushing all of its mass into an infinitely small point, where space-time ceases to behave as we understand it. However, the extreme conditions within a singularity are beyond the current capabilities of our laws of physics. Neither general relativity nor quantum mechanics can fully describe what occurs within such an environment. As a result, singularities remain one of the greatest puzzles in modern physics. This inherent mystery comes to a head with the concept of the event horizon, the boundary beyond which nothing, not even light, can escape the gravitational pull of a black hole. This makes direct observation of singularities impossible. Much of what we know about them comes from theoretical models, solutions to Einstein's equations, such as the Schwarzschild solution for non-rotating black holes and the Kerr solution for rotating ones. Singularities do not merely exist as isolated cosmic anomalies. They may also hold the key to understanding the birth of the universe itself. It's theorized that the Big Bang, our universe's inception, may have arisen from a singularity, suggesting that the universe emerged from a point of infinite density and curvature. This concept blurs the lines between the known and the unknown, beckoning us toward a new frontier of understanding. Singularities are not just relics of the past, but perhaps the very fabric from which time, space, and all of existence unfurled. As we grapple with the complexities of these cosmic phenomena, the singularity challenges the very foundation of our theories. They force us to confront profound questions about the nature of reality. What happens when the gravitational forces are so intense that the structure of space-time itself is distorted beyond recognition? In the context of general relativity, a singularity represents a catastrophic breakdown of the fabric of space-time, causing the usual laws governing the universe to become irrelevant. This breakdown of predictability and causality forces physicists to reconsider everything we know about the cosmos. One of the greatest implications of singularities is their role at the heart of black holes. At the center of every black hole lies a singularity, hidden behind the event horizon. If you were to continue falling into a black hole, you would eventually reach a point where space and time bend so radically that no known physics can predict what comes next. Classical physics fails entirely at this point, rendering our understanding incomplete. This prompts the pursuit of a theory that unites the two pillars of modern physics, general relativity and quantum mechanics, in an effort to understand these cosmic anomalies. The quest for quantum gravity, a theory that could unite these two realms, remains one of the most profound challenges in theoretical physics. Singularities may not only provide insight into the structure of black holes and the cosmos, but also reveal the deep underlying connections between space, time, and the forces that shape the universe. Could singularities hold the key to understanding the very origins of our universe and the forces that govern it? These questions remain unanswered, yet they continue to drive exploration in physics, pushing us toward a more unified and complete understanding of reality itself. Singularities are not isolated curiosities. They might have been instrumental in the formation of the universe. Their role in the origins of space-time, the birth of galaxies, and the evolution of the cosmos continues to stir debate. As we venture further into the mysteries of the universe, these phenomena challenge our imagination, urging us to explore the limits of our knowledge and perhaps to redefine what we think we know about space, time, and the very nature of existence. The Big Bang Theory suggests that our universe emerged from an incredibly hot, dense state, which in itself could be seen as a form of singularity. If the universe truly expanded from a point of infinite density, then exploring singularities could unlock profound insights into both the origin and ultimate fate of everything around us. The very act of understanding singularities might lead to the revelation of new paradigms in physics, challenging and revising our current understanding of space-time, causality, and the very fabric of the cosmos. This pursuit is at the forefront of scientific exploration, carrying the potential to completely reshape the foundational principles of physics and provide answers to some of the deepest mysteries of our existence. What lies beyond the event horizon of a black hole remains one of the most captivating enigmas in astrophysics. This boundary, which surrounds a black hole, is a point of no return. Once anything crosses this threshold, whether light, matter, or even information, it is pulled inward, unable to escape. The sheer gravitational forces within the event horizon compress matter to unimaginable densities, driving everything towards the singularity at the black hole's core. At this core, physics as we know it breaks down. Here lies a point of infinite density, where the usual rules of the universe no longer apply. Inside the event horizon, the very concepts of space and time undergo dramatic transformations, according to Einstein's theory of general relativity. Space and time essentially swap roles. Time flows inexorably toward the singularity, much as we experience the flow of space in our everyday lives. This mind-bending change suggests that for someone falling into a black hole, no matter how they attempt to navigate the situation, their journey would inevitably lead to a collision with the singularity. This would occur in a finite amount of proper time, regardless of their actions. Theories about the fate of anything that reaches the singularity range from the suggestion that matter is crushed into an infinitely small point, to more speculative ideas involving quantum foam or other exotic states of matter that defy our current understanding of physics. Some even propose that what lies beyond the event horizon might connect to other parts of the universe, or to entirely different universes, through what are known as wormholes. These hypothetical bridges through space-time could potentially offer passages to completely different realms, sparking imaginations, but remaining, for now, purely theoretical due to the enormous practical and conceptual challenges involved. Adding another layer of complexity is the concept of Hawking radiation, introduced by the renowned physicist Stephen Hawking. This revolutionary idea suggests that black holes are not completely isolated, sealed-off regions as once thought. Instead, quantum effects near the event horizon may cause black holes to emit radiation, leading them to lose mass gradually and eventually evaporate. This radiation hints at deeper, unexpected connections between the black hole's interior and exterior, further complicating the mystery of what truly lies beyond the event horizon. Ultimately, the very nature of what exists past this boundary challenges the fundamental pillars of physics, forcing us to confront the gaps in our knowledge. It demands a unified theory that combines general relativity with quantum mechanics, an endeavor that could revolutionize our understanding of space-time, the cosmos, and perhaps even the nature of existence itself. In contrast to black holes, there is the theoretical concept of white holes. These hypothetical solutions to Einstein's equations of general relativity represent the exact opposite of black holes. While black holes are regions where nothing can escape due to their extreme gravitational pull, white holes are imagined as regions where nothing can enter. The notion of white holes, like black holes, remains a tantalizing mystery, purely theoretical at this stage, but opening fascinating possibilities in the realm of cosmology. Imagine a cosmic phenomenon so mysterious, so paradoxical, that it seems to defy the very laws of physics as we know them. A celestial object that expels matter and energy, yet from which nothing can approach. This is the essence of a white hole. If black holes are the ultimate cosmic vacuum cleaners, pulling in everything that crosses their event horizon, then white holes are their polar opposites. These theoretical entities eject matter and energy from their event horizon, preventing anything from entering. The concept of white holes emerges naturally from the equations of general relativity, which, fascinatingly, are time reversible. If you were to reverse the flow of time around a black hole, you'd find that it transforms into a white hole. This suggests that, in theory, for every black hole there could be a corresponding white hole. But while black holes are well-established entities in our universe, white holes remain a purely theoretical curiosity, one that has yet to be observed or confirmed. White holes are often linked with another mind-bending concept: wormholes. These theoretical passages in space-time are envisioned as tunnels connecting distant points across the universe, or even between different universes. In this speculative framework, one end of the wormhole might be a black hole, and the other end could be a white hole. This would theoretically allow matter to travel through the wormhole, entering via the black hole and exiting through the white hole. But while this idea is tantalizing, it comes with a significant catch. These wormholes would likely be highly unstable, collapsing in on themselves almost instantaneously under the influence of extreme gravitational forces. The very existence of white holes would also challenge our understanding of the fundamental laws of thermodynamics, particularly the second law, which states that in a closed system, entropy, or disorder, tends to increase over time. White holes, by expelling matter and energy, would seem to reduce entropy, creating a paradox. If white holes exist, or could exist, this would necessitate a radical revision of our understanding of time and the laws governing the flow of energy and matter. Despite their intriguing theoretical foundation, white holes differ significantly from their counterparts, black holes. A black hole is a region in space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. This gravitational pull results from the collapse of a massive star's core, leading to the formation of a singularity, an infinitely dense point surrounded by the event horizon. Anything that ventures too close is inevitably pulled in, disappearing from the observable universe. Conversely, a white hole acts as the time-reversed counterpart of a black hole. While a black hole's event horizon marks a boundary beyond which nothing can escape, a white hole's event horizon marks a boundary beyond which nothing can enter. Instead of pulling in matter, a white hole expels it, theoretically preventing anything from crossing inward. In essence, while a black hole acts as a cosmic sink, a white hole would function as a cosmic fountain, ejecting matter and energy into the universe. The differences between these two phenomena also extend into their roles within our understanding of space-time. Black holes are supported by a wealth of astronomical evidence, from the detection of gravitational waves produced by black hole mergers to the imaging of the event horizon by the Event Horizon Telescope. These observations provide solid confirmation of black holes' existence. White holes, on the other hand, remain firmly in the realm of speculation. They have not been observed, and no empirical evidence supports their existence. For now, they primarily exist within the mathematical models of theoretical physicists. An intriguing aspect of this difference lies in the relationship between black holes, white holes, and entropy. Black holes possess entropy, as described by physicists Jacob Bekenstein and Stephen Hawking. This entropy is proportional to the area of their event horizons, aligning with the second law of thermodynamics, which dictates that the total entropy of a closed system cannot decrease. White holes, by contrast, would theoretically exhibit a decrease in entropy by expelling matter and energy, directly contradicting this law. This paradox alone makes the existence of white holes deeply problematic within our current understanding of thermodynamics. Some theoretical frameworks even explore the possibility that black holes and white holes could be connected via wormholes, forming bridges in space-time. These wormholes would allow matter to enter a black hole and emerge from a white hole. However, such ideas remain purely speculative. This, as wormholes, if they exist at all, would likely be highly unstable and collapse almost immediately under the immense gravitational forces at play. While black holes are well-documented entities, white holes remain purely hypothetical, expelling matter and energy and preventing any external influence from crossing their event horizon. Their differences highlight not just the mysteries of the universe, but the deep complexities of space, time, and the very fabric of reality itself. The story of white holes is one of curiosity, paradox, and a reminder of how much we have yet to discover about the universe. Pushing the boundaries of modern physics and cosmology, the idea of white holes emerges as a fascinating, though speculative, counterpart to the more well-known black holes. Theoretical evidence for white holes primarily arises from the complex mathematical frameworks within general relativity. At the core of this concept lies the time reversal symmetry inherent in the equations that govern the fabric of our universe. Imagine reversing the direction of time in the Schwarzschild solution, one of the simplest descriptions of a non-rotating black hole. The result? A white hole. This time reversal symmetry suggests that, according to Einstein's theory, white holes are just as theoretically viable as black holes. Within the extended framework of general relativity, the concept of white holes becomes even more intriguing. When we examine solutions such as the maximally extended Kruskal-Sekaris coordinates for a Schwarzschild black hole, a more complete picture emerges. These coordinates not only describe the black hole, but also introduce a white hole region. In this extended spacetime model, the diagram reveals two distinct regions: the black hole, where objects are drawn in, and the white hole, from which objects would theoretically emerge. While mathematically consistent, this model is, for now, purely theoretical. No empirical evidence supports the physical existence of these fascinating constructs. The notion of white holes also surfaces in the context of quantum gravity and black hole singularities. One of the most exciting speculative theories is loop quantum gravity, which suggests that classical singularities within black holes may not be the end of the story. Instead, quantum effects might replace them, allowing matter inside a black hole to rebound and explode outward, transforming the black hole into a white hole. This transformation creates an elegant bridge between the worlds of quantum mechanics and general relativity, offering a possible resolution to the enigmatic relationship between the birth and death of stars. Further adding to the mystery of white holes is their role in discussions surrounding the black hole information paradox, a problem that challenges the very principles of quantum mechanics. The paradox questions whether information that falls into a black hole is lost forever, violating the fundamental laws of physics. White holes, in theory, could provide a resolution by acting as a mechanism for releasing the information trapped inside a black hole, thus preserving the integrity of information conservation laws. Although this idea is still speculative, it presents a tantalizing avenue for further exploration. Despite their theoretical elegance, it is critical to highlight that no observational evidence has yet been found to support the existence of white holes. They remain compelling ideas within the mathematical structure of general relativity and speculative theories, pushing the limits of our understanding of spacetime, gravity, and the universe itself. These ideas invite further inquiry into the fundamental nature of reality, urging scientists to question and challenge our current understanding of the cosmos. An even more intriguing speculation connects white holes to the concept of wormholes, hypothetical tunnels that could link distant points in spacetime. A wormhole, often referred to as an Einstein-Rosen bridge, is envisioned as a tunnel-like structure that might allow for shortcuts across the universe. In certain theoretical models, one end of a wormhole might be a black hole pulling in matter and light, while the other end could be a white hole, expelling matter and preventing anything from entering. This idea is rooted in the same mathematical principles of general relativity that describe both black holes and white holes. In such a model, an object could potentially enter the black hole end, travel through the space-time tunnel, and emerge from the white hole end, creating an astonishing potential for interstellar travel. Though still firmly within the realm of theoretical physics, the concept of white holes continues to challenge our understanding of space-time and gravity. Their speculative nature only adds to their allure, urging physicists to venture further into the unknown in hopes of uncovering the true nature of our universe. However, this idea is riddled with challenges and profound implications. One of the most significant hurdles lies in the inherent instability of wormholes. The immense gravitational forces at the black hole end of a wormhole cause it to collapse almost instantaneously, creating an impractically short-lived tunnel. This would make it nearly impossible for anything, be it matter or even information, to traverse through it. In addition, keeping a wormhole open long enough for travel requires exotic matter with negative energy density, a concept that, though theoretically permissible, has yet to be observed empirically. This adds yet another layer of complexity to the already speculative notion of traversable wormholes. Interestingly, the connection between wormholes and white holes brings us into the realms of both cosmology and quantum physics. Some speculative theories propose that our universe might have been birthed from a white hole in a different region of space-time, or even another universe. If this theory holds, the Big Bang could be conceptualized as a white hole event, one that expelled matter and energy, forming the very fabric of our cosmos. In the context of quantum gravity, particularly in theories like loop quantum gravity, there is the radical suggestion that black holes might transition into white holes as a result of quantum effects. These transitions might manifest as a bounce at the singularity, where the collapsing matter's quantum state reverses, transforming into an expanding white hole. This concept attempts to sidestep the paradoxes inherent in classical black hole theories, such as the singularity and the information loss paradox. In summary, while the connection between white holes and other regions of spacetime through wormholes paints an intriguing theoretical picture, it is still very much confined to the speculative and mathematically elegant domain of modern physics. The practical realization of such concepts faces enormous, perhaps insurmountable, scientific and observational challenges. However, these ideas continue to inspire groundbreaking work in theoretical physics, pushing us to rethink and expand our understanding of space-time and the universe itself. White holes, considered the time-reversed counterparts of black holes, remain some of the most enigmatic and controversial concepts in cosmology. While black holes are known for their immense gravitational pull that draws in everything around them, white holes are theorized to expel matter and energy, vehemently refusing entry to anything, even light. Some scientists speculate that white holes could form under extreme conditions in the universe, potentially acting as the other side of a black hole, creating an exit point. If this were true, they could play a pivotal role in the cosmic order, redistributing matter and energy throughout space, contributing to the balance of the cosmos. The link between white holes and the early universe is equally fascinating. Some hypotheses propose that white holes could provide an explanation for the rapid spread of matter and energy during the early stages of the universe. Though we have yet to find direct evidence of their existence, the idea of a white hole process may help explain how our universe emerged in a higher dimensional space. These theories push the limits of our understanding of space-time, urging us to reconsider what we think we know about the structure and behavior of the cosmos. As speculative as these ideas may be, their inclusion in cosmological models challenges fundamental assumptions about the nature of time, space, and the interconnectedness of the universe. Bubble universes, a captivating concept within the multiverse theory, suggests that our universe may be but one bubble among an infinite number of others in a vast cosmic foam. According to the theory of eternal inflation, different regions of spacetime might inflate at different rates. While some regions stop inflating, they form distinct bubbles, each one containing a universe with its own set of physical laws, constants, and even dimensions of time and space. Imagine our universe as a solitary soap bubble, floating in a boundless sea of other bubbles, each encapsulating a unique universe with potentially unknown and fascinating properties. The boundaries between these bubble universes are of particular interest. If two bubbles were to collide, it could create observable effects in our universe, potentially explaining certain anomalies detected in the cosmic microwave background radiation. Though we have no direct evidence for bubble universes, the mathematical frameworks supporting their existence are consistent with our current understanding of quantum mechanics and general relativity. The notion of bubble universes challenges us to consider a much larger and more complex tapestry of existence, where our universe is just one part of an endlessly branching, evolving multiverse. This concept not only stretches the limits of scientific imagination, but also raises profound questions about the true nature of reality itself. In exploring these concepts, we are forced to confront our current understanding of the universe and reality as we know it. With each new theory and discovery, we inch closer to understanding the unimaginable vastness of the cosmos. What lies beyond our comprehend today may one day unlock answers to some of the universe's most perplexing mysteries. In this captivating exploration of the universe, we journey into the realm of bubble universes, a concept deeply intertwined with the theory of eternal inflation. This theory proposes that shortly after the Big Bang, space-time itself expanded at an incredibly fast exponential rate, driven by a high-energy field known as the inflaton field. This initial surge in expansion laid the groundwork for the formation of multiple, distinct universes within the ever-growing fabric of space. As the inflaton field fluctuates due to quantum mechanical effects, certain regions experience a slowdown in inflation, creating pockets or bubbles of normal spacetime. Each bubble that forms becomes an independent universe with its own set of physical laws, constants, and even fundamental properties. Imagine a vast cosmic landscape where each bubble universe is like a unique island in an infinite sea of inflating space. These universes evolve and branch off, creating a multiverse, a never-ending process of universe creation that continues today. The process of bubble formation arises from the complex dynamics of the inflaton field. As the field decays, it produces various vacuum states, each with different energy levels. In some regions, the inflaton field finds a low energy state and halts inflation, leading to the birth of a bubble universe. In other regions, inflation continues for longer periods, creating vast expanses of space between these emerging universes. The model of eternal inflation suggests that our own universe, though seemingly finite, is only one of many in this constantly expanding cosmic structure. The formation of bubble universes isn't just a theoretical curiosity, it's a fundamental part of the ongoing process of cosmic evolution. This continual bubbling off of new universes happens all the time, much like droplets forming and falling from a fountain, creating an endless stream of new realities within the vast, inflating space. The question is, how can we prove these universes exist? The evidence for bubble universes is still largely theoretical, derived mainly from the mathematical framework of cosmology and quantum mechanics. One of the strongest pieces of evidence comes from the very theory of eternal inflation. The equations describing inflation predict that inflation doesn't cease uniformly everywhere. Instead, inflation slows down in certain regions, forming isolated pockets, each a potential bubble universe, while inflation continues in the vast spaces between them. If eternal inflation is correct, then the formation of bubble universes is not just possible, but practically inevitable. Intriguingly, the cosmic microwave background, CMB radiation, might provide us with indirect clues about the existence of these bubbles. The CMB is the afterglow of the Big Bang, and anomalies or temperature irregularities in this radiation could suggest past interactions or collisions between our bubble universe and others. These anomalies, while subtle, could offer a glimpse into the chaotic and complex processes of cosmic collisions. Advanced telescopes, such as the Planck satellite, are continuously probing these irregularities, hoping to uncover the fingerprints of ancient cosmic events that might hint at the existence of neighboring universes. String theory adds yet another layer of complexity, allowing for the existence of multiple dimensions and a vast array of potential vacuum states, each one giving birth to a distinct universe. Theoretical physicists use this framework to model how bubble universes might arise by interacting with one another in unexpected and fascinating ways. Although these ideas are conceptually profound, they remain without empirical confirmation, presenting one of the most thrilling challenges in modern cosmology. If the existence of bubble universes is verified, the implications for our understanding of reality would be staggering. Perhaps the most mind-boggling possibility is the potential for interaction between these universes, particularly through collisions. As bubbles expand, they could meet, merging their surfaces in dramatic cosmic events. In the context of cosmology, these collisions could leave traces on the fabric of spacetime, detectable as distinct patterns in the CMB. Such collision zones might also give rise to exotic structures, domain walls, or other high-energy interfaces that could influence the formation of galaxies, stars, and even the fundamental constants that define the laws of physics in each universe. These cosmic scars could be evidence of the profound interconnectedness between universes, offering a tantalizing glimpse into a multiversal reality. Scientists are eager to find signs of these interactions in the CMB, as even the smallest anomaly could serve as proof of these grand multidimensional collisions. But there's more. Quantum entanglement, a phenomenon where particles can be instantly correlated across vast distances, might allow for instantaneous communication between different bubble universes. This concept, though highly speculative, suggests a form of interconnectedness that defies classical understanding. Imagine, if you will, particles in one universe affecting those in another, regardless of the vast cosmic distances separating them. Though these ideas are currently beyond our ability to test directly, they represent a frontier in theoretical physics, pushing the boundaries of what we know about space, time, and the very nature of existence. The notion that our universe is just one chapter in an unfathomably vast multiversal story is as exhilarating as it is perplexing, challenging us to rethink everything we thought we knew about the cosmos. In this ever-expanding multiverse, we might be but a single bubble in a vast sea of possibilities, where each universe offers a new chapter in the story of creation. The search for evidence of these bubble universes, their collisions, and their potential connections continues to captivate the minds of cosmologists and physicists alike. The journey to uncover these cosmic truths has just begun, and the implications for our understanding of the universe and everything beyond it are bound to be revolutionary. The implications of bubble universes for our understanding of the cosmos stretch far beyond the boundaries of current science, offering profound and transformative insights into reality and existence itself. At the core of this idea lies the suggestion that our universe is not unique, but merely one among an infinite number of bubble universes, each with its own distinct physical laws and constants. This notion challenges the very fabric of our understanding, pushing us to reconsider what we thought we knew about the universe. Instead of perceiving our cosmos as a singular, isolated entity, we must now consider it as part of a vast, interconnected multiverse, where each universe operates under its own rules, potentially shaping different versions of reality. This shift in perspective opens up new avenues for addressing the fine-tuning problem. If there exist multiple universes with properties that vary widely, it's conceivable that at least one universe would naturally evolve conditions that could support life as we know it. The very notion that there could be an infinite variety of universes offers a solution to one of the deepest mysteries of cosmology. Why does our universe seem so finely tuned to support life? Perhaps the answer lies in the existence of other universes, where the odds of life-friendly conditions occurring are simply higher. Moreover, bubble universes provide us with a tantalizing new view of spacetime. The theory of eternal inflation suggests a constantly expanding universe, punctuated by pockets of space where inflation halts, allowing new universes to take shape. This view reimagines the birth of our universe not as a one-off event, but as part of an ongoing cosmic process. The boundaries of what we understand as our observable universe could be just one speck in a much larger, eternally evolving cosmos. It even beckons questions about what might lie beyond what we can see, potentially linking the mysterious realms of quantum mechanics with the more familiar world of general relativity in ways that were once considered impossible. The very concept of multiple universes also directly challenges the anthropic principle, which argues that the universe must be designed to support life because we exist to observe it. In a multiverse, however, this principle loses its relevance. In such a scenario, we simply find ourselves in one of the bubble universes that happens to support life, without needing to posit some grand design. This recontextualization alters our understanding of our place in the cosmos, pushing us away from anthropocentric explanations and encouraging a more probabilistic view of the universe's existence. It's a shift that could redefine everything we know about life's origins, fine-tuning, and the vastness of reality. At the same time, the simulation hypothesis brings a different yet equally revolutionary challenge to our understanding of reality. It posits that our universe might not be real at all, but a highly advanced simulation created by an intelligent civilization. This idea, though initially speculative, gained traction through the work of philosopher Nick Bostrom, who argued that it is statistically likely we are living in a simulated world. The hypothesis rests on three core assumptions. Either civilizations don't survive long enough to develop the technology for simulation, they choose not to create simulations, or we are already living in one. If the first two propositions are false, the third is almost certainly true, according to Bostrom. This raises profound philosophical and ethical questions about existence, consciousness, and free will. If we are indeed in a simulation, what does that mean for our understanding of our lives and experiences? The creators of such a simulation would have godlike control over the rules governing our universe, manipulating everything from the laws of physics to the very fabric of time and space. In a sense, we could be living inside a virtual reality so detailed that it is indistinguishable from true existence. Although the simulation hypothesis remains speculative and lies at the intersection of philosophy and cutting-edge science, it has sparked intense discussions among scientists, technologists, and thinkers. Advances in artificial intelligence, computational power, and virtual reality make these ideas more relevant than ever. We're on the cusp of developing technologies that could one day allow us to create our own simulations. If true, the simulation hypothesis would shatter our conventional understanding of existence and raise profound questions about the nature of consciousness, free will, and the ultimate purpose of life. The idea of a simulated universe also implies that our reality could be a product of highly advanced computational processes. Imagine a world where every interaction, particle, and force is meticulously simulated by computers with unimaginable processing power. Such a civilization would need to master not just macroscopic elements like stars and planets, but also the intricate dance of quantum particles. Quantum mechanics, with its probabilistic nature and phenomena like entanglement, could be a reflection of underlying programming mechanisms optimizing resources, much like a video game engine renders only the parts of the world the player interacts with. This brings us to the limitations we observe in our own universe. Could the speed of light be a constraint in the simulation's processing power? Might dark matter and dark energy be artifacts of underlying computational rules we haven't yet understood? The more we look, the more anomalies appear, suggesting that our understanding of the cosmos may be incomplete, maybe even simulated, forcing us to reconsider the nature of existence itself. The implications of both bubble universes and the simulation hypothesis stretch across the very foundations of physics, cosmology, and our existential beliefs. These concepts challenge the very core of what we thought we knew about the universe and our place in it, opening up new possibilities and redefining our understanding of reality. As we explore these fascinating ideas, we are forced to confront our deepest questions about life, consciousness, and the true nature of the cosmos. And as we continue to push the boundaries of science and technology, who knows what we may discover next in the endless, uncharted territories of existence. The discovery of a pixel-like structure in space-time, or the identification of fundamental limits to information processing within the universe, could serve as potential clues, pushing us to consider the possibility that our reality might be simulated. But the challenge remains. How can we prove or disprove this hypothesis? Currently, there is no empirical evidence to confirm such an idea, primarily because it teeters on the edge of unfalsifiability. It is, after all, incredibly difficult to conceive of an experiment that would definitively validate or debunk the notion. Yet, despite this, the very notion of a simulated reality opens up an entire realm of philosophical and scientific dialogue, encouraging us to explore the boundaries of our understanding of existence, consciousness, and technology. The concept of simulation theory, while compelling, remains speculative and philosophical at its core, rather than firmly grounded in empirical science. However, various intriguing threads of reasoning and indirect evidence have emerged to support the possibility that we might indeed be living in a simulated environment. One such line of thought revolves around the computational limits that seem to exist within the very fabric of our universe. For example, the finite speed of light and the quantized nature of spacetime can be seen as reminiscent of a digital system, with the universe functioning much like a grid of pixels or a video game's refresh rate. These limitations may not simply be a byproduct of the universe's physical laws, rather, they could be necessary constraints imposed by the underlying computational resources required to maintain the simulation. Another powerful argument in favor of the simulation hypothesis comes from what is known as fine-tuning, the uncanny precision of the physical constants of our universe. Take, for example, the gravitational constant, the charge of an electron, or the cosmological constant. These values appear to be finely tuned to allow for the existence of life. Some proponents of the simulation hypothesis suggest that this fine-tuning could be the result of deliberate design, a trait often associated with software programs crafted with specific outcomes in mind. Within this framework, our universe might be viewed as a meticulously controlled environment, optimized for particular outcomes, much like a video game world designed to yield specific experiences for its players. Furthermore, certain peculiarities within the realm of quantum mechanics, particularly phenomena like entanglement and superposition, offer additional fodder for those who support the simulation hypothesis. One of the most striking aspects of quantum mechanics is the observer effect, where particles exist in a state of probability until they are observed or measured. Some researchers have likened this behavior to a computer program that only renders certain aspects of a scene when they are needed, conserving computational resources. This approach mirrors modern video games, where the game engine renders only what is visible to the player at any given moment, improving processing efficiency. However, despite the thought-provoking nature of these arguments, they remain circumstantial, largely open to interpretation, and most importantly, they lack definitive empirical evidence. The simulation hypothesis is still very much a philosophical and theoretical issue, rather than one that has gained widespread scientific consensus. While advanced technology, future discoveries, or new breakthroughs in theoretical physics could eventually provide the clarity we seek, for now, the idea of living in a simulation remains a captivating lens through which we can examine the nature of reality itself and ponder the deeper questions about our existence. As we continue to push the boundaries of knowledge and technology, perhaps we'll uncover more answers, or even new questions that challenge the very foundation of what we know about the universe and our place in it. Proponents of the simulation hypothesis frequently draw comparisons between our universe and the vast intricate worlds of computer simulations or virtual environments. This analogy helps explain phenomena such as the mysterious edge of the universe, a concept that has long intrigued cosmologists. One approach to understanding this enigma is to propose that the edge we perceive may actually be a boundary set by the computational limits of the simulation itself. In much the same way that video games create boundaries beyond which players cannot venture, the universe might have been designed with an inherent limit to contain the simulation within manageable computational constraints. From this viewpoint, the observable universe, an immense sphere approximately 93 billion light-years in diameter, could be likened to the rendered portion of a video game world. As a player approaches the outer limits of the game, the world becomes sparse or increasingly undefined. Likewise, the universe might exhibit diminishing detail the closer we get to its edge, possibly even lacking any rendered universe beyond this point, because it serves no purpose for us, the simulated beings. In other words, if we cannot observe or interact with it, there's no need for it to exist in full detail. This could explain why we haven't observed anything definitive beyond this edge. Simply put, The data isn't there because it doesn't need to be. Another intriguing theory proposes that the edge is not a hard boundary, but rather a transition zone to another phase of the simulated environment. This is akin to entering a new level or dimension within a video game. The new phase could operate under completely different physical laws and constants, or it might simply be a void, an area where the simulation runs in a minimalist state to conserve computational resources. This notion, while highly speculative, offers a fascinating alternative to the conventional view of the universe's boundaries. It hints at the possibility of an entire new realm existing just beyond our reach, waiting to be unlocked, much like an undiscovered level in a game. It's crucial to note that these ideas, while captivating, remain highly philosophical and speculative. They offer imaginative explanations of the universe's structure, but they lack empirical evidence to support them. Yet these interpretations compel us to think about cosmological boundaries in ways we haven't before. They encourage a fresh dialogue across multiple disciplines, from cosmology and physics to computer science and philosophy. While traditional cosmology continues to focus on observable evidence and theoretical models, the simulation hypothesis pushes the boundaries of our imagination, offering a provocative framework that challenges our understanding of reality. The philosophical implications of the simulation hypothesis are as vast as they are profound. If our reality is truly a simulation, it fundamentally alters how we perceive authenticity and existence itself. One of the most immediate questions that arises is epistemological in nature. How reliable is our knowledge? If our understanding of the universe is shaped by the rules and limitations of a simulation, could it be inherently flawed? Our empirical observations, based on scientific experimentation and sensory perception, might be incomplete or even misleading, bound by the artificial rules designed by the creators of the simulation. This casts doubt on the veracity of everything we perceive, making our experiences contingent on the simulation's design rather than any objective reality. In addition to questions about the limits of knowledge, the simulation hypothesis also raises significant inquiries about consciousness. If our minds, thoughts, and experiences can be simulated by a computer, does this mean that consciousness itself is merely a byproduct of complex algorithms? Or does consciousness require something more, a physical, non-simulatable substance that transcends computational processes? This line of questioning intersects with age-old debates in the philosophy of mind, such as the nature of dualism versus materialism, and whether machines could ever possess genuine subjective experiences. If consciousness can emerge from computational processes within a simulation, it would support the notion that consciousness might be substrate independent, meaning it could exist wherever there is sufficient processing power and complexity, regardless of the medium. The ethical and existential ramifications of the simulation hypothesis are equally staggering. If we are indeed inhabitants of a simulated world, then the beings who created and control the simulation must possess godlike powers over our reality. This realization forces us to confront profound questions about the intentions of these creators. Are we part of a grand experiment, a source of entertainment, or perhaps an educational program? What moral responsibilities do these creators have toward us, and what purpose lies behind our simulated existence? Are we simply passive players in a game, or do we possess the agency to change the rules of the simulation? These questions, though speculative, are essential to the ongoing conversation about the nature of reality, consciousness, and existence. They remind us that the boundaries of our understanding are not fixed, but are constantly being pushed both by scientific discovery and philosophical inquiry. The simulation hypothesis serves as a provocative lens through which we can challenge our deepest assumptions about the universe and our place within it. Whether we are living in a simulated environment or not, these questions encourage us to re-examine what it means to be conscious, to exist, and to truly understand the nature of the cosmos. The idea that our lives and even the universe itself could be manipulated, paused, or even terminated at the whim of external entities challenges the very essence of our existence. This concept, once purely the domain of science fiction, begins to stir an unsettling thought. Are we truly in control of our fate, or is there a larger, unseen force pulling the strings? It taps into an underlying sense of existential vulnerability, a fear that the universe, the forces that govern it, and even our lives might be subject to something beyond our comprehension. But perhaps the most unsettling aspect of this concept lies in its intersection with age-old religious and metaphysical questions. If we are living in a simulation, as the hypothesis suggests, what does that mean for the nature of creation? Do our creators, who would have the power to manipulate and alter our reality, hold a role akin to that of deities? This notion challenges our traditional religious and spiritual beliefs, offering a modern technological twist on questions humanity has been asking for millennia. The simulation hypothesis not only calls into question the nature of reality, but it might just upend our understanding of existence itself, altering our very relationship to the divine, creation, and purpose in ways we are only beginning to grasp. Amid this cosmic uncertainty lies one of the universe's greatest mysteries: dark matter. This elusive substance, making up about 27% of the universe's total mass and energy content, has fascinated scientists for decades. But unlike the matter we are familiar with, stars, planets, and even dust, dark matter is invisible. It doesn't emit, absorb, or reflect light. Its presence is not directly observed. Rather, it is inferred through its gravitational effects on visible matter, radiation, and the very structure of the cosmos itself. For example, the rotation curves of galaxies provide a striking illustration of dark matter's unseen influence. Stars situated at the outer edges of galaxies are observed to move faster than would be expected based on the gravitational effects of visible matter alone. This discrepancy led scientists to hypothesize the existence of an invisible mass, dark matter, that exerts an unseen gravitational pull on the stars and galaxies around it. This is just the beginning of the story. Dark matter's effects ripple throughout the universe, shaping its very structure from the very moment of its creation. In the early universe, fluctuations in the density of dark matter served as seeds, around which galaxies and even galaxy clusters would form. Without dark matter's gravitational pull, it is believed that large-scale cosmic structures like galaxies would not have formed in the way they did, or perhaps not formed at all. As the universe expanded, dark matter's role became even more critical, helping to mold and guide the visible matter into the intricate cosmic web that we observe today. In fact, one of the key pieces of evidence for dark matter comes from the phenomenon of gravitational lensing. When light from distant galaxies passes near a massive object like a galaxy cluster, the light bends due to the gravitational pull of that object. But in many cases, the amount of bending observed exceeds what can be explained by visible matter alone, suggesting the presence of dark matter in these regions. Scientifically, dark matter is classified into two broad categories: cold dark matter, which moves at relatively slow speeds, and hot dark matter, which moves at speeds close to the speed of light. Most of the evidence points to cold dark matter being the dominant form, made up of slow-moving heavy particles that have yet to be directly detected. Candidates for dark matter particles include weakly interacting massive particles, WIMPs, and axions, but despite extensive research and experimental efforts, no direct detection has been made thus far. The mystery of dark matter continues to be one of the most pressing challenges in cosmology and particle physics. However, despite the lack of direct detection, we know that dark matter plays a fundamental role in the way the universe is structured. It acts as an invisible scaffolding, guiding the formation of galaxies, clusters of galaxies, and larger cosmic structures. The gravitational effects of dark matter are essential for understanding how matter is distributed on a grand scale, and they offer a crucial window into the underlying forces that govern the cosmos. As we look back to the early universe, just moments after the Big Bang, it is dark matter that provided the initial seeds from which the universe began to take shape. Tiny quantum fluctuations in dark matter's density would eventually grow, attracting gas and dust, which over billions of years coalesced to form galaxies and clusters. Without dark matter, the universe's story would be vastly different. Ordinary matter alone could not have clumped together to create the complex structures we now see. Simulations that incorporate dark matter reveal the intricate cosmic web that underpins the universe. These simulations show vast filaments of dark matter connecting empty regions of space with galaxies forming at the intersections of these filaments. This web-like structure has been confirmed through large-scale astronomical surveys, validating the predictions of these simulations and giving scientists greater insight into the very architecture of the cosmos. Ultimately, dark matter's influence on the universe cannot be overstated. It is the invisible force that governs the way galaxies form, the way stars are born, and the way the universe continues to evolve. As we uncover more about this mysterious substance, we move one step closer to understanding the fundamental forces that shape our reality, and perhaps even the very nature of existence itself. Moreover, dark matter plays a crucial role in maintaining the stability of galaxies. When scientists observe the rotation curves of galaxies, plots showing the velocity of stars at varying distances from the galactic center, a fascinating anomaly becomes apparent. Stars in the outer reaches of galaxies are moving far faster than would be expected based solely on the gravitational pull of visible matter. This unexpected speed points to the presence of a hidden force, one that cannot be seen directly, but is responsible for the extra gravitational pull: dark matter. This invisible substance provides the necessary gravitational influence to prevent stars in the outer regions from flying off into space. In galaxy clusters, dark matter's gravitational pull is even more pronounced. It binds galaxies together, counteracting the centrifugal forces caused by their rapid rotation. Without dark matter, these galaxies would simply tear themselves apart. The invisible matter's gravitational effects stretch far beyond individual galaxies, influencing vast swaths of the universe. Perhaps one of the most striking manifestations of dark matter's presence comes through a phenomenon known as gravitational lensing. When the light from distant objects passes through a massive galaxy cluster or dark matter-rich region, the light bends. This bending of light distorts, magnifies, and sometimes even creates multiple images of the same object. These lensing effects act as cosmic maps, revealing the hidden distribution of dark matter throughout the universe. They have proven to be invaluable in helping astronomers map the shape of our universe, providing us with essential insights into its underlying structure. Dark matter is indeed a cornerstone of cosmic structure. It is fundamental to the formation and stability of galaxies, and plays a key role in shaping the large-scale architecture of the universe. Its gravitational influence is the anchor that holds the cosmos together, helping to weave the complex tapestry of matter and light that we observe as the night sky. Without dark matter, the universe as we know it would look vastly different, with stars and galaxies unable to maintain the delicate balance that allows them to exist. In stark contrast to dark matter, there exists another mysterious force that permeates the universe: dark energy. Comprising about 68% of the universe's total energy content, dark energy is believed to have a repulsive effect, one that drives the accelerated expansion of the universe. This discovery, which began to take shape in the late 1990s, was the result of observations of Type 1a supernovae. These exploding stars appeared dimmer than anticipated, suggesting they were farther away than expected in a decelerating universe. The data revealed an astonishing conclusion. The expansion of the universe was not slowing down as once thought, but accelerating. This unexpected acceleration pointed to the existence of an unknown energy component, later dubbed dark energy. While the precise nature of dark energy remains elusive, it is generally modeled in one of two primary ways. The first is the cosmological constant, a concept first introduced by Albert Einstein in his equations of general relativity. The cosmological constant represents a uniform energy density that fills space, causing the universe to expand at an accelerating rate. This model aligns well with current observational data, such as studies of the cosmic microwave background radiation and surveys of the large-scale structure of the universe. The second model treats dark energy as a dynamic, changing field, often referred to as quintessence. In this view, dark energy's density is not constant but fluctuates over time, potentially offering a different mechanism for the universe's accelerating expansion. While this idea offers intriguing possibilities, it also introduces greater complexity and additional parameters that must be understood. Researchers are also investigating other theories, including potential modifications to our understanding of gravity and alternative approaches to general relativity. The implications of dark energy stretch far beyond our current understanding of the universe. If its influence continues to dominate, the universe's expansion could continue indefinitely. This would result in a big freeze, a scenario in which galaxies drift farther apart, stars burn out, and the cosmos slowly becomes a cold, empty, and desolate place. The ultimate fate of the universe may, therefore, rest in the hands of dark energy, a mysterious force that shapes not only the present, but also the future of everything in existence. Alternatively, variations in dark energy could lead to startlingly different outcomes, such as a Big Rip scenario, where the universe's accelerating expansion eventually tears apart everything in its path. Galaxies, stars, planets, and even atomic matter could be torn asunder. The true nature of dark energy remains one of the most significant puzzles in cosmology, yet it is crucial for a complete understanding of the universe's evolution. Ongoing and future research, particularly from cutting-edge observatories like the UCLID spacecraft and the James Webb Space Telescope, promises to illuminate this mysterious force, potentially revolutionizing our comprehension of the universe's most fundamental properties and its ultimate fate. Dark energy plays a pivotal role in the accelerated expansion of the cosmos, working in opposition to the gravitational forces that would otherwise slow down this expansion. The first key piece of evidence for dark energy came from the observation of distant Type 1a supernovae in the late 1990s. Researchers discovered these supernovae were unexpectedly dimmer and farther away than anticipated in a universe where the expansion should have been decelerating. This shocking result pointed to the fact that, contrary to previous beliefs, the expansion of the universe began accelerating about 5 billion years ago. The way dark energy affects the universe's expansion can be likened to a repulsive force that permeates all of space. This force pushes galaxies away from each other more rapidly over time, in contrast to the attractive gravitational pull of ordinary and dark matter. Instead of drawing objects together, dark energy creates an anti-gravity effect. This concept is reflected in Einstein's cosmological constant, initially introduced in his equations of general relativity. Einstein originally included the cosmological constant to model a static universe, but he discarded it after discovering that the universe was expanding. Modern observations, however, have brought the idea back into the spotlight, showing that a positive cosmological constant could explain the observed acceleration in the universe's expansion by providing a consistent energy density spread uniformly throughout space. Another approach to understanding dark energy treats it not as a static constant, but as a dynamic field known as quintessence. In this model, dark energy's density changes over time and across different regions of space, potentially offering a more intricate explanation for the accelerating expansion. Despite this alternative, the cosmological constant remains the simplest and most widely accepted explanation for dark energy's influence on the universe. The implications of dark energy extend far beyond the present. They are crucial to understanding the universe's future. If dark energy continues to dominate the expansion, the universe will keep accelerating, possibly leading to a big freeze. In this scenario, galaxies will move so far apart that stars will exhaust their fuel, leaving behind a cold, dark, and empty universe. However, if dark energy changes in ways we don't yet understand, other scenarios may unfold, such as the Big Rip. This would see the accelerating expansion tear apart galaxies, stars, planets, and even atomic matter itself, as space itself stretches. Dark energy's role in cosmic expansion is vital for understanding both the past and future of the universe. As researchers continue to refine their models and enhance observational techniques, the enigmatic nature of this force will hopefully come into clearer view. Imagine for a moment journeying to the very edge of the universe, where galaxies are but faint whispers of light against an overwhelming dark backdrop. Here, the invisible forces of dark matter and dark energy play their parts in shaping the cosmos. Dark matter, which makes up about 85% of the total mass of the universe, acts as the unseen scaffold upon which galaxies are built. Though it neither emits nor absorbs light, its gravitational pull can be detected through the motion of stars within galaxies. Without dark matter, galaxies would simply disintegrate, They're stars scattered across the cosmos like marbles from a broken net. In this sense, dark matter ensures the structural integrity of galaxies, holding them together even at the farthest reaches of the universe. However, beyond just providing a cosmic glue, dark matter's true role and nature remain largely hidden, awaiting further exploration. As we venture deeper into the cosmos, these mysterious forces, both dark energy and dark matter, continue to challenge our understanding of the universe's origin, structure, and destiny. Their investigation promises to uncover profound insights into the very fabric of reality. In the vast, mysterious expanse of the universe, there exists an invisible force that exerts its power, unseen yet undeniable. This force, known as dark energy, is an enigma, one that thrusts galaxies apart and is believed to make up nearly 70% of the cosmos. Think of it as the universe's cosmic anti-gravity. It is the force that accelerates the expansion of the universe, driving galaxies away from each other at ever-increasing speeds. This astonishing revelation came in the late 20th century when scientists made an unexpected discovery. Rather than the universe's expansion slowing down, it was speeding up. At the edge of the observable universe, dark energy plays a pivotal role, driving galaxies into an ever-widening abyss, stretching the very fabric of space-time itself. As it pushes galaxies farther apart, it triggers a future that seems increasingly distant and cold. While dark matter provides the gravitational glue that holds the cosmic structures together, dark energy pushes against it, driving everything toward a chilling fate. One possible future is the Big Freeze, where the galaxies and stars will be so far apart that the universe will become a cold, dark, and distant expanse, a hauntingly quiet place with no stars or galaxies left to shine. This unimaginable vastness of the cosmos leads us to one of the most profound and tantalizing pursuits in modern physics, the search for a theory of everything, TOE. This theory aims to unify the four fundamental forces that govern our universe: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces shape everything from the tiniest particles to the grandest cosmic structures. A successful theory of everything would seamlessly merge the principles of general relativity, which explains gravity and the large-scale structure of space-time, with the peculiar and often paradoxical world of quantum mechanics, which governs the behavior of subatomic particles. So far, no single theory has managed to bridge this vast chasm, but two leading candidates have emerged. String theory and loop quantum gravity are the front runners in this cosmic race. String theory proposes that the fundamental building blocks of the universe are not tiny, point-like particles, but rather minuscule, vibrating strings. Each vibration corresponds to a different particle, much like the strings on a musical instrument that produce different notes when plucked. These strings reside in multiple dimensions, beyond the familiar 3 dimensions of space and 1 of time. On the other hand, loop quantum gravity takes a different approach. It aims to quantize space-time itself, suggesting that both space and time are made up of discrete loops. This theory doesn't rely on the continuous fabric of space-time that general relativity describes, but rather posits that at the smallest scales, the universe is granular and made of indivisible units. Both theories offer profound insights, but they are not without their challenges, and they do not yet provide a universally accepted solution. Despite these hurdles, the search for a theory of everything remains a quest of immeasurable importance. The answers that lie within this pursuit could unlock a deeper understanding of the universe and its origins. Imagine for a moment a world where the macroscopic and microscopic realms of existence are unified under one grand theory, a theory that could potentially explain everything from the behavior of galaxies to the motion of subatomic particles. At the boundary where the cosmic and quantum realms intersect, traditional physics falters. General relativity struggles to account for the intense gravitational forces at the scale of black holes, while quantum mechanics is too probabilistic to explain large-scale cosmic phenomena. The theory of everything seeks to reconcile these realms, providing a cohesive framework that accounts for the forces governing both the infinitely large and the infinitely small. String theory offers a particularly compelling perspective on this cosmic edge. It suggests that the universe's fundamental particles may not be tiny points, as we once thought, but rather vibrating strings. These strings oscillate at specific frequencies, and each unique vibration corresponds to a different particle. In this view, the universe's edges may not be the limits of space itself, but projections from higher dimensional spaces. These extra dimensions, invisible to our senses, could influence how the universe behaves at its outermost reaches. One of the most captivating ideas emerging from this theory is the concept of cosmic brains, hypothetical multidimensional objects that could serve as boundaries or interfaces between different regions of the universe. These brains could reveal entirely new layers of the cosmos, offering a glimpse into the true nature of the universe's edges. With ideas like these, string theory pushes the boundaries of our understanding, providing a framework where the universe's vastness is only the beginning of its mysteries. In the scientific community, two leading contenders vie for the title of theory of everything. Both string theory and loop quantum gravity aim to bridge the divide between general relativity and quantum mechanics, but they approach the problem in fundamentally different ways. String theory proposes that the universe is built from one-dimensional strings, and their vibrations produce all of the particles and forces we observe. On the other hand, loop quantum gravity suggests that the very fabric of space-time is quantized, composed of discrete loops that form the underlying structure of the cosmos. The search for a theory of everything is far from over. Each day, scientists continue to explore these theories, hoping to unlock the deepest secrets of the universe. The discovery of such a theory would mark a profound leap in our understanding of the cosmos, revolutionizing our view of reality in ways that could only be imagined just a century ago. As the quest for this ultimate theory continues, the mysteries of dark energy and the edges of the universe await to be unraveled. In the quest to unlock the universe's deepest secrets, two revolutionary theories stand at the forefront: string theory and loop quantum gravity. These theories aim to answer one of the most elusive questions in physics: what is the fundamental structure of the universe? While both provide intriguing possibilities, they diverge dramatically in their approaches, each offering distinct pathways toward a theory of everything, TOE, the ultimate framework capable of unifying all forces of nature. String theory, with its elegant mathematical structure, introduces a vision of the cosmos that goes far beyond the familiar three spatial dimensions and one of time. According to this theory, there are additional unseen dimensions, possibly more than 10, woven into the very fabric of reality. These extra dimensions are compactified, curled up so tightly that they remain imperceptible to our current methods of experimentation. Within string theory lies M theory, which proposes an 11-dimensional universe where not only strings but also membranes or brains exist. These brains, massive objects in their own right, coexist with strings, offering a radically new view of the universe. One of string theory's greatest appeals is its potential to unify all the fundamental forces of nature: gravity, electromagnetism, the weak force, and the strong force, into a single elegant framework. However, the allure of string theory comes with a major trade-off: its reliance on extra dimensions and complex, often abstract mathematics that make it extraordinarily difficult to test experimentally. Despite its sweeping promise of a unified theory, string theory faces challenges that prevent it from being confirmed through traditional scientific methods, which is a significant limitation. Nevertheless, its mathematical beauty and ability to explain previously unconnected phenomena keep it at the center of theoretical physics. On the other hand, loop quantum gravity, LQG, takes a radically different approach by focusing on the quantization of space-time itself. Unlike string theory, which treats space-time as a smooth, continuous entity, LQG proposes that space-time is granular, composed of discrete loops that form a quantum structure at the smallest scales. These loops are not just theoretical constructs, but actual quantum states of the gravitational field. LQG's most profound contribution is its potential to resolve the problem of quantum gravity, how gravity behaves at the quantum level. It does so without requiring extra dimensions, offering a more conservative approach that remains closer to our observable reality. Loop quantum gravity also presents a novel solution to understanding the quantum properties of black holes and the Big Bang singularity, offering insights into the birth of the universe and the extreme environments found at its edges. However, LQG is not without its own set of challenges. While it avoids the complications of extra dimensions, it struggles with the integration of the other fundamental forces beyond gravity. This lack of unification makes it more difficult to extend LQG into a comprehensive theory of everything. Still, it remains an essential contender in the search for a unified theory, offering a grounded and discrete view of the universe's most fundamental structure. The ambition of a theory of everything is not merely to stand as an isolated monument to theoretical physics. Instead, it is about creating a framework that integrates seamlessly with existing cosmological theories. KETOE must not only unify the forces, but also explain phenomena across all scales, from the infinitesimally small particles of quantum mechanics to the vast structures of the cosmos itself. For example, the Big Bang theory, which suggests that the universe began as an incredibly hot and dense singularity roughly 14 billion years ago, posits that the universe has been expanding ever since. A TOE would delve into the quantum aspects of this singularity, potentially offering a deeper understanding of the conditions that led to the Big Bang. In this context, string theory could provide valuable insights into the pre-Big Bang era. Through its higher dimensional models and the interactions of brains, string theory may offer a coherent picture of the events that triggered the Big Bang. In contrast, loop quantum gravity introduces the concept of a quantum bounce. This idea suggests that before the current expansion of our universe, a previous universe may have contracted to a point and then bounced, beginning a new cycle of expansion. This quantum bounce aligns with cyclic models of the universe, providing a quantum physics-based explanation for the creation of our cosmos. Moreover, a TOE has the potential to offer significant contributions to our understanding of cosmic inflation, the rapid expansion of the universe that occurred just after the Big Bang. Both string theory and loop quantum gravity have the tools to probe this period, offering different but complementary views of the universe's early moments. In conclusion, while both string theory and loop quantum gravity present fascinating yet radically different visions of the universe, they share a common goal: to uncover the unified framework that governs all of existence. Whether through the elegant, high-dimensional universe of string theory or the granular, loop-based structure of loop quantum gravity, each theory pushes the boundaries of what we know about the cosmos. And though they face significant hurdles, they represent the next step toward unraveling the mysteries of the universe, a step that may one day lead us to the ultimate theory of everything. The rapid expansion of the universe in the moments following the Big Bang set the stage for the vast cosmos we observe today, a phenomenon that still captivates physicists. The initial inflationary period, occurring in fractions of a second, fundamentally altered the structure of the universe. String theory's landscape, which proposes an intricate array of possible vacuum states and dimensions, might hold the key to understanding the energy dynamics that fueled this inflation. This theory presents the idea that the various configurations of fields in string theory could correlate with different inflationary models, providing a basis for testable predictions, especially regarding the cosmic microwave background radiation. Meanwhile, the theory of loop quantum gravity suggests that space-time itself is not continuous, but rather discrete, offering a granular structure to the universe during its rapid expansion. This view could lead to observable phenomena, such as primordial gravitational waves, imprinted upon the fabric of space-time from that very early period. As the quest to integrate these theories with existing cosmological models continues, it not only promises a more unified understanding of the universe's birth and evolution, but also seeks to resolve profound puzzles, including the nature of dark matter and dark energy. The prospect of a theory of everything, TOE, could revolutionize our understanding of these mysterious components that together account for about 95% of the universe's mass energy content. Dark matter and dark energy, though detected primarily by their gravitational effects, remain elusive. A TOE could provide a clear explanation of their true nature and interactions, offering a comprehensive view of their roles in the cosmic tapestry. This breakthrough would likely reshape our models of galaxy formation, the expansion of the universe, and even influence the ultimate fate of all cosmic structures. Beyond solving these long-standing enigmas, a TOE could provide groundbreaking insights into the realm of black holes, offering the potential to bridge the divide between general relativity and quantum mechanics. Understanding phenomena such as Hawking radiation and the black hole information paradox would not only advance theoretical physics, but could also unlock practical technologies far beyond our current scope. The exploration of these cosmic phenomena could reveal technologies that change the way we live, much as quantum mechanics led to the development of modern electronics. On a grander scale, a TOE could redefine our conception of space-time itself, revealing the ultimate laws that govern reality. By understanding the universe at the most fundamental level, we could shift our perception of existence, transforming our views on everything from the fabric of space-time to the subtle dance of subatomic particles. Philosophically, such a theory would offer a cohesive narrative of the universe's origin, structure, history, and destiny. It would provide answers to questions that have puzzled humanity for millennia. Practically, the implications of a TOE would extend far beyond theoretical physics. Just as quantum mechanics unlocked the world of electronics, a deeper understanding of the universe could lead to technological advancements that we can scarcely imagine today. These advances could revolutionize energy sources, material science, and our very understanding of what is possible. The realization of a theory of everything would mark a monumental leap in humanity's pursuit of knowledge. It promises not just scientific enlightenment, but profound shifts in how we live, think, and explore the mysteries of the cosmos. As we strive for a unified understanding of the universe, we are embarking on a journey that could alter the course of human history, propelling us into realms of discovery previously thought unreachable. Exploring the edge of the universe through the lens of various religious perspectives offers a captivating glimpse into the rich diversity of human beliefs and the many ways different faiths interpret the cosmos. While the concept of a physical edge to the universe is a modern scientific curiosity, many religious traditions present their own metaphysical or symbolic understandings of boundaries and existence itself. These perspectives invite us to explore the universe not just as a physical realm, but as a place where the spiritual and the material converge. In Christianity, the universe is viewed as the intentional creation of an omnipotent God. The Bible may not provide specific details about the physical structure or edge of the universe in the way that modern science does, but it suggests a finite creation governed by divine will. In Genesis 1 verse 1, it says, "In the beginning, God created the heavens and the earth," which implies a universe that is both purposeful and ordered. While the Bible often refers to the heavens in spiritual rather than physical terms, it establishes the concept of boundaries, not in a scientific sense, but in the understanding that God's sovereignty extends beyond what humans can comprehend. This heavens signifies a realm that transcends the physical cosmos, an infinite and ultimate boundary where God's dominion reigns supreme. Moving to Hinduism, the universe is seen as an eternal cycle, created, preserved, and destroyed by the divine trinity of Brahma, Vishnu, and Shiva. Rather than a fixed boundary or edge, Hindu thought presents the cosmos as an ever-flowing manifestation of Vishnu, constantly changing through the dance of Shiva. The boundaries of the universe in Hinduism are not physical but metaphysical, reflecting transitions between states of consciousness and existence. The cosmic cycles, creation, preservation, and destruction, are seen as part of a larger, infinite reality. This view allows for the notion of many realms within the vast cosmic ocean, where each layer of reality offers a unique perspective on existence. The idea of an edge, then, is fluid, not bound by physical dimensions, but by the capacity for spiritual awakening. Buddhism, with its focus on inner realms of consciousness and the journey toward enlightenment, offers yet another perspective on the universe's boundaries. In Buddhist thought, the physical dimensions of the cosmos hold less significance than the spiritual and mental landscapes one navigates through meditation. The idea of an edge in Buddhism is symbolic, representing the limits of individual perception and the mental barriers that must be transcended to reach nirvana. The ultimate reality, or nirvana, is beyond the physical constraints of the cosmos, emphasizing the journey toward liberation from suffering, ignorance, and the cycle of rebirth. The Buddhist understanding of the universe, therefore, is less about the vastness of space and more about the vastness of the mind. In Islam, the universe is similarly viewed as the creation of an all-powerful God, Allah. While the Quran does not explicitly address the physical edge of the universe, it speaks to the vastness and meticulous order of the cosmos, describing the heavens and the earth as part of Allah's grand design. Everything within the universe is subject to God's will, and his knowledge and power extend beyond any physical frontiers. The concept of an edge in Islam, therefore, is not about the physical limit of space, but about the boundary where human understanding ends and divine wisdom begins. Allah's will and knowledge are infinite, and the true edge of the universe is where the mysteries of the cosmos meet the divine. These religious interpretations offer a rich and varied tapestry of thought on the concept of the universe's edge. Blending physical, metaphysical, and spiritual dimensions, they invite us to consider the cosmos not only as a physical space, but as a reflection of deeper, more profound realities. They remind us that the quest to understand the universe is as much an inward journey of self-discovery as it is an outward exploration of space. The search for answers about the edge of the universe in a religious context is intertwined with the search for meaning and purpose in life itself. Whether through the lens of Christianity, Hinduism, Buddhism, or Islam, these perspectives suggest that the true boundary of existence may not lie in the stars above, but within the heart and soul of each individual, waiting to be explored. Christianity, in particular, offers a perspective that intertwines the concept of the universe's edge with the theological worldview of creation, divine order, and the omnipresence of an all-powerful God. The Bible, although silent on the specifics of the physical boundaries of the universe, provides a framework through which believers can contemplate the cosmos. Genesis 1:1. In the beginning, God created the heavens and the earth, is foundational to the Christian understanding of the universe, suggesting that the cosmos was created by God's divine will. This verse affirms that the universe has purpose and order established by God. Though it does not venture into the scientific specifics of the universe's dimensions, it underscores the idea that the cosmos is finite and created for a divine purpose, a creation that exists under the watchful care of a sovereign God. The physical dimensions of the universe may be beyond human comprehension, but in Christianity, it is understood to be a creation that is always under the authority and power of God. As we continue our exploration of the universe's edge, the diverse religious viewpoints invite us to consider that what we often regard as limits in our material world may be far less absolute than we think. Instead of seeing these boundaries as physical lines that confine us, we might begin to see them as spiritual thresholds, waiting for us to cross and discover new realms of existence, understanding, and faith. Whether we turn to scripture, philosophy, or inner contemplation, the edge of the universe, in both the literal and symbolic senses, offers a powerful invitation to seek, learn, and grow. In the vast tapestry of religious thought, the concept of the universe's boundaries holds a special place. However, the way various traditions interpret these boundaries can vary greatly. Instead of presenting a literal view of the cosmos, many religious texts use poetic and metaphorical language to describe the universe. This approach emphasizes the sovereignty and omnipotence of the divine. For example, the Bible presents the cosmos as a magnificent creation, a divine masterpiece that speaks volumes about God's majesty. In Psalm 19, verse 1, we read, "The heavens declare the glory of God. The skies proclaim the work of his hands." This verse paints a vivid picture of the universe as a testament to divine craftsmanship, where every star, planet, and galaxy bears witness to the greatness of the Creator. It is not merely a physical realm, but an expression of God's glory. The concept of the edge of the universe in Christian thought is not to be taken literally. Rather, it serves as a symbol of human limitations, the boundary beyond which human understanding fails. It reflects the point at which earthly knowledge gives way to the profound mysteries of divine wisdom. Verses such as Isaiah 40, verse 22, which speaks of God sitting enthroned above the circle of the earth, and Job 26, verse 7, describing God as stretching the northern sky over empty space and suspending the earth over nothing, underscore the awe-inspiring and immeasurable nature of God's creation. These passages point to the boundlessness of the cosmos and the mystery surrounding it, suggesting that while the universe may have physical boundaries, they are beyond human comprehension. Only God possesses the complete knowledge of the cosmos. Christianity goes a step further, positing an ultimate reality that transcends the physical universe. Beyond the stars and planets, beyond the reach of telescopes and human exploration, there is an eternal realm. This concept of eternal life and a heavenly realm is central to Christian theology. Revelation 21:1 speaks of a new heaven and a new earth, which alludes to an existence beyond the finite boundaries of the known universe. This new reality is depicted as a place where God's presence is fully realized, a realm where believers are united with the divine. It's a vision not limited by time, space, or physical boundaries, but one that is full of eternal promise and divine fellowship. In this light, Christianity views the edge of the universe not as a literal endpoint, but rather as a metaphor for the limits of human understanding. The focus is less on the specifics of where the universe ends and more on the glorification of God as the creator and sustainer of all existence, both seen and unseen, finite and infinite. Hinduism offers a remarkably different yet equally profound view of the universe. Rooted in ancient cosmological wisdom, Hinduism weaves together physical cosmology with deep metaphysical concepts. Unlike the linear and finite perspectives that are often prevalent in Western thought, Hindu cosmology embraces the cyclical nature of time in the universe. According to Hindu belief, the universe is created, preserved, and destroyed in an eternal cycle. This cycle is governed by the three main deities of the Hindu trinity: Brahma, the creator; Vishnu, the preserver; and Shiva, the destroyer. Brahma's creation of the universe spans billions of years, forming what is known as a Day of Brahma, followed by an equally long period of dissolution known as the Night of Brahma. These heavens, though not described in scientific terms, are understood to represent vast, layered realms that exist beyond our earthly experience. Each heaven is thought to possess unique characteristics, possibly even inhabitants, which reveal the complex, intricate structure of God's divine creation. Though the Quran does not provide a detailed scientific breakdown, it emphasizes the grandeur and perfection of God's work, inviting believers to reflect on the vastness of existence and the unseen realities beyond our comprehension. In Islamic eschatology, the belief in realms beyond the physical world plays an essential role. The concept of akhirah, or the hereafter, is integral to Islamic teachings, positing that after death, souls transition to a different plane of existence. Within this plane lie realms such as Jannah, paradise, and Jahannam, hell, which are richly described in the Quran and Hadith literature. These realms serve as the ultimate destinations for souls, where they are rewarded or punished based on their actions in life. Paradise is depicted as a place of eternal bliss, where gardens, rivers, and palatial dwellings await the righteous, as found in Surah Al-Baqarah 2:25, and give good tidings to those who believe and do righteous deeds, that they will have gardens in paradise beneath which rivers flow. On the other hand, hell is portrayed as a place of unimaginable suffering, where the consequences of one's deeds in the physical world are fully realized. Furthermore, Islam introduces the concept of the ghaib, or the unseen, which encompasses not only the realms of paradise and hell, but also other spiritual beings and dimensions that remain beyond the reach of human perception. The ghaib includes angels, jinn, and supernatural forces that interact with the material world, but exist primarily in realms imperceptible to human senses. The Quran frequently encourages belief in the unseen as a critical expression of faith, emphasizing that God's creation extends far beyond the limits of human understanding and perception. This concept invites Muslims to embrace the mysteries of the world, acknowledging the unseen forces that shape their lives and guide their spiritual journey. Through these teachings, Islam offers a rich and profound understanding of the universe, one that encompasses realms far beyond the physical world. The seven heavens, the hereafter, and the domain of the ghaib each contribute to a broader framework of divine creation. These beliefs serve to illustrate the complexity and vastness of God's creation, highlighting that the physical universe we experience is but a single facet of a much grander, multifaceted reality that exists under the watchful eyes of the divine. This view, while distinct from the empirical approach of modern cosmology, aligns with mystical and esoteric traditions that suggest there is much more to existence than what meets the eye, a reality that is both intricate and awe-inspiring, crafted by the infinite creator. Across various cultures and spiritual systems, the idea of higher planes of reality has been a consistent and fascinating theme. These realms, which transcend our ordinary sensory experiences, are often viewed as domains of greater spiritual or metaphysical complexity, each governed by its own unique characteristics and laws. As humanity has explored the mysteries of the universe, many teachings suggest that these higher planes are not distant, unreachable realms, but dimensions that are accessible through inner transformation, spiritual practices, and heightened states of consciousness. In Western esoteric traditions, such as theosophy, the concept of multiple layers of existence is deeply ingrained. Mystics like Emanuel Swedenborg contributed to the understanding of a multi-layered universe, one that goes beyond the physical world to encompass various levels of consciousness. Theosophy in particular maps out a series of planes: the physical, astral, mental, and spiritual realms. Each plane corresponds to different forms of existence, from the densest, most material physical world to higher, more subtle, and ethereal spiritual dimensions. The astral plane, often associated with emotions and desires, is believed to be a realm where thoughts and feelings have tangible effects. Ascending through these realms, the mental plane is where intellectual thought takes center stage, characterized by logical reasoning and rationality. But beyond these lies the higher spiritual planes, where one can experience a profound sense of unity with the divine. In this context, these planes are not mere abstract concepts, but are perceived as transformative spaces that lead individuals toward a greater understanding of their divine nature. In Eastern philosophies, similar teachings resonate with remarkable depth and detail. Hinduism, for example, describes a cosmology with a hierarchy of worlds, from the earthly Bhuloka to the higher celestial realms of Svargaloka. These realms are inhabited by gods, sages, and advanced spiritual beings. The idea of these planes being stages of spiritual evolution is central to many Hindu beliefs. In Buddhism, the concept of the Bhavacakra, or Wheel of Life, depicts various realms of existence, each representing different states of consciousness and moral development. From hellish realms to heavenly realms, the Buddhist path to enlightenment involves navigating these planes of existence, with each stage bringing the practitioner closer to the realization of their true nature and ultimate liberation. Sufi mysticism, a rich and profound tradition within Islam, offers its own unique interpretation of higher planes. Sufi teachings explore the journey of the soul through various stages, known as stations or maqamat, as it strives toward ultimate union with the divine. This process involves traversing subtle realms of consciousness, often referred to as the lataif, which serve as intermediary spaces that allow the seeker to transcend material reality. These stages reflect different aspects of spiritual development, leading one through layers of inner reality until they attain a state of spiritual perfection and unity with God. Mysticism, across traditions, consistently emphasizes that these higher planes are not merely external spaces, but are, in fact, states of being that can be directly experienced within. Practices such as meditation, prayer, rituals, and the cultivation of virtues are considered vital in purifying the mind and soul, helping individuals ascend through these planes. The mystical path ultimately leads to deeper insight, enlightenment, and an understanding of one's oneness with the greater cosmic reality or divine essence. Ultimately, these mystical and esoteric teachings converge on a profound truth. The universe is not a flat material world, but a multi-dimensional tapestry of interconnected realities. Each layer of existence represents a higher form of spiritual awareness and understanding, providing seekers with a dynamic and evolving journey toward enlightenment. These higher planes are more than just philosophical or metaphysical concepts. They offer a map for personal transformation, guiding individuals toward their highest spiritual potential and an intimate connection with the divine. Philosophical inquiries into the nature of the universe continue to explore these questions of reality's multi-layered existence. These inquiries not only seek to understand the physical properties and origins of the cosmos, but also delve into the deeper metaphysical implications of our existence. What is the purpose of the universe? What is our place in it? These questions have echoed throughout human history, inviting all who are willing to look deeper into the nature of reality to consider the profound interconnectedness of all things. As we seek answers, the journey itself becomes a path toward greater wisdom, understanding, and ultimately a deeper connection to the divine order of the universe. One of the most profound questions that has occupied human thought for centuries is the very nature of reality itself. Philosophers have long debated whether the universe is fundamentally composed of physical matter and energy, or whether it is dualistic, incorporating both material and immaterial aspects, such as the mind or spirit. This inquiry into the nature of existence often expands into deeper questions about the nature of consciousness. Is consciousness an emergent property of physical processes in the brain, or does it point to a deeper, non-material reality beyond the observable world? These questions lie at the heart of many of the most important philosophical discussions. Furthermore, the origins of the universe remain a central puzzle. What existed before the Big Bang, if anything? Classical physical theories struggle to address such inquiries because they view time and space as having originated with the Big Bang itself. From a philosophical perspective, this gives rise to the intriguing question of whether the universe had a first cause, often invoking theological interpretations. The cosmological argument for the existence of God is one such response, suggesting that the universe's existence must have a creator. However, other theories challenge this notion, proposing an eternal or self-causing universe that operates outside the boundaries of causality and time as we know it. Another deep philosophical question asks, why does the universe exist at all? Why is there something rather than nothing? This existential query, famously posed by philosopher and mathematician Gottfried Wilhelm Leibniz, delves into metaphysical considerations about the very nature of existence. Can the universe's existence be explained by necessity, chance, or design? Is there a deeper purpose that underpins all of creation? These questions do not merely seek answers, they challenge us to rethink our very place in the vast cosmos. The philosophical exploration of reality also leads us to ponder the laws that govern the universe. Are these laws intrinsic to the fabric of the cosmos, or are they the result of some external force or principle, perhaps even the will of a higher mind? The fine-tuning of the universe, the remarkably precise values of physical constants that allow life to exist, only adds layers to this debate. Is this fine-tuning a mere coincidence, a necessity of the laws of nature, or evidence of intentional design? This is the essence of the anthropic principle, which has given rise to heated debates within both cosmology and theology. At the forefront of these discussions is the multiverse theory, which suggests that our universe may be only one of an infinite number of universes, each with different physical laws and constants. This raises a host of philosophical questions. If every possible outcome exists somewhere in the multiverse, does this mean that our universe is just one of many iterations of reality? How does this idea impact our understanding of causality, identity, and the very nature of existence itself? Time and space, too, remain central to the ongoing philosophical inquiry. Is time simply a linear progression from the past to the future, or is it, as some have proposed, an illusion, an emergent property of consciousness and perception? Or perhaps time is cyclical, repeating itself in endless loops. Similarly, are space and time fundamental aspects of reality, or are they emergent properties dependent on more basic principles that we have yet to comprehend? These questions touch upon the groundbreaking work of both renowned physicists and philosophers as we continue to probe the mysteries of the universe. Philosophical discussions about the nature of the universe encompass a broad array of issues, from the fundamental nature of reality to the origins and purpose of the cosmos, to the very laws that govern existence. These inquiries do not only aim to solve scientific puzzles, they seek to enrich our understanding of our place in the cosmos and to offer deeper meaning to our existence. Philosophers blend scientific knowledge with metaphysical and epistemological considerations, weaving together a complex tapestry of ideas that reflect the limits of human understanding. From a metaphysical standpoint, philosophers have long questioned whether the universe has any true boundaries. Some argue that the universe is infinite, extending infinitely in both space and time. This view challenges the very concept of end and leads to further inquiries. What does it mean for space to be infinite, and how does that alter our understanding of existence itself? How does one even begin to grasp the implications of such an infinite expanse? On the other hand, some theories propose that the universe is finite, yet closed, a concept supported by certain interpretations of general relativity. In this model, space curves back on itself, much like the surface of a sphere. According to this view, if one were to travel far enough in a straight line, they would eventually return to their point of origin. This model blurs the lines between boundaries and the absence of boundaries, suggesting that the universe's limits may exist only in our perception, not in any physical reality. These philosophical inquiries, spanning topics as vast as the nature of consciousness and the origins of the universe, provide a powerful lens through which to explore the mysteries of existence. As humanity delves deeper into understanding the cosmos, these discussions will continue to evolve, offering new insights and raising fresh questions about the true nature of reality itself. Epistemologically, philosophers have long been captivated by the mysteries of human knowledge and its limits, particularly regarding the vast expanse of the universe. Our understanding of reality is constrained by the observable phenomena around us and the limits of the instruments we use to perceive them. This observable universe is often defined by the furthest distance from which light has had time to reach us since the Big Bang, acting as a cosmic horizon beyond which we cannot peer due to the finite speed of light. However, this observable slice of reality may only be a small fraction of a far grander and more mysterious whole. The true extent of the universe could vastly surpass this observable portion, thus introducing an element of the unknown into our quest for understanding. In this respect, philosophers like Immanuel Kant have proposed that the boundaries of human knowledge may be fundamentally shaped by the structures of human cognition itself. Kant suggested that our understanding of concepts like space and time are not universal truths, but are instead deeply embedded in the way our minds perceive and organize reality. According to this view, the ultimate nature and full extent of the universe may be inherently beyond our grasp, limited by the very nature of our cognitive faculties. This introduces an intellectual dilemma. Is there a limit to what we can know about the universe, or are we simply constrained by the frameworks we use to understand it? Another crucial dimension of this conversation is the notion of conceptual boundaries, the limits imposed by the language and frameworks we use to define our understanding of the universe. Philosophers have long debated how the way we conceptualize and define terms influences how we perceive reality. If, for instance, we define the universe as all that exists, it becomes inherently paradoxical to consider an outside to the universe. If there is nothing beyond all that exists, how can the concept of a boundary even make sense? This brings us to one of the most profound philosophical questions. Can anything lie beyond the universe? Or does the universe, by its very definition, encompass all of existence? In cosmology, this question is further complicated by the theory of the multiverse. If our universe is only one of many, it challenges the traditional view of cosmic boundaries. The boundaries of our universe may not be absolute, but rather relative to the existence of other universes within a multiverse. Philosophers are now exploring the implications of this model, whether these universes interact, and if so, how they define the limits of reality itself. This idea forces us to reconsider the very idea of a boundary. Are we talking about a cosmic edge, or simply a border that is defined in relation to other realms? The complexity of defining the boundaries of the universe continues to unfold through various philosophical lenses. Some philosophers take an infinite view of the cosmos, proposing that space and time extend boundlessly, while others argue for a more finite model, one in which the universe is a closed system with distinct limits. Adding to this, epistemological reflections, including the limitations of human cognition, bring into question the very possibility of grasping the full extent of the universe. Theories of the multiverse, in particular, blur these boundaries. intertwining the empirical with the metaphysical in ways that challenge our most fundamental assumptions. What does it mean then to ask about what lies outside the universe? When we define the universe as all that exists, the question of the outside becomes paradoxical. How can we speak of anything outside of the totality of existence itself? In one sense, this question invites us to examine our assumptions about space, time, and reality. From a metaphysical perspective, when we ask what is outside the universe, we may be grappling with the very limits of human understanding, limits that are shaped by the structures of our cognition and language. Just as a two-dimensional being might have no concept of outside on the surface of a sphere, we may be unable to grasp what lies beyond the confines of our three-dimensional experience. Philosophers, in their pursuit of truth, often suggest that such a question may be a misunderstanding, an attempt to apply spatial concepts to something that transcends those boundaries. The notion of outside may simply be a projection of our own spatial limitations. The true nature of existence, it could be argued, may be beyond our comprehension, confined not to the spatial dimensions we know, but to a different realm entirely. Some philosophical and theological traditions propose that what lies outside the universe may not be physical at all, but rather something entirely non-material, a realm of pure consciousness, abstraction, or even divinity. For example, in various religious traditions, it is posited that God or a divine presence exists outside of the universe in a manner that transcends the physical dimensions we understand. This exteriority is not spatial in nature, but ontological. It represents a different kind of reality, one that interacts with the universe in ways that are profoundly beyond the scope of our physical senses and concepts. In summary, the question of the boundaries of the universe serves as a profound philosophical inquiry, blending the empirical with the metaphysical. Whether considering the limits of human cognition, the frameworks of conceptual understanding, or the possibility of a multiverse, philosophers continue to explore the nature of the universe's boundaries, both the ones we can observe and the ones we can only imagine. As we peer into the cosmos, we are reminded of how much we still have to learn about the true extent of existence and the limits of our knowledge. The concept of the multiverse has long intrigued both scientists and philosophers alike, sparking discussions that reach far beyond the boundaries of traditional cosmology. The term multiverse refers to the radical idea that our universe is not a singular entity, but rather one of many universes, each potentially governed by its own distinct laws of physics, dimensions, or fundamental constants. This theory envisions a vast multiversal framework where universes coexist in parallel, each occupying its own unique space within the greater cosmos. From a scientific perspective, the idea that there could be other universes existing beyond our own poses fascinating possibilities. It fundamentally challenges our understanding of what constitutes the universe. Historically, the universe has been considered the entirety of existence, the all-encompassing realm of space, time, matter, and energy. However, with the concept of the multiverse, we are forced to reconsider that definition. What if the universe we inhabit is only one component in a grander, more complex structure? In this scenario, our universe becomes just one facet in a sprawling cosmic mosaic, possibly offering insight into phenomena that might have been previously beyond our comprehension. Philosophically, the question of what lies beyond our universe has intrigued thinkers for centuries. The limits of human knowledge and language play a crucial role in shaping our understanding of such abstract concepts. Immanuel Kant, the eminent German philosopher, posited that the human mind is structured in such a way that it cannot perceive the thing in itself, the true nature of reality beyond our sensory experiences. This idea challenges the very core of human cognition, suggesting that there are aspects of existence, including what may lie outside the universe, that are inherently beyond our grasp. In this sense, the multiverse theory may be seen as a metaphor for our epistemological boundaries, reflecting the limits of what can be known or even conceived within our cognitive frameworks. This line of inquiry, questioning what exists beyond the universe, touches upon a multitude of areas: metaphysics, theology, and epistemology. The very act of questioning the boundaries of our universe forces us to reconsider our concepts of space, existence, and reality. It raises profound metaphysical questions about the nature of being and the possibility of other forms of existence. At the same time, it invokes theological musings about the purpose and structure of creation, as well as the possibility of a divine or transcendent reality that lies outside the physical universe. And on an epistemological level, it forces us to confront the limits of human understanding. Are there things that simply cannot be known, or are there methods of inquiry yet to be discovered? This interplay between science, philosophy, and theology forms a rich tapestry of intellectual exploration, where the boundaries of our conceptual and perceptual frameworks are pushed to their utmost limits. Each discipline informs and challenges the others, offering new insights and raising new questions. Philosophical perspectives have historically played a vital role in shaping the scientific worldview, influencing the development of scientific theories and methodologies, and even guiding the interpretation of empirical data. This dynamic relationship between science and philosophy is essential in understanding the origins, structure, and ultimate fate of the universe. One of the key contributions of philosophy to scientific thought lies in its provision of conceptual foundations for scientific inquiry. The very notion of natural laws that govern the behavior of matter and energy throughout the universe, is rooted in philosophical thinking. Ancient Greek philosophers like Aristotle and Pythagoras envisioned a cosmos ordered by rational, discoverable principles. This idea of an orderly universe, governed by predictable laws, laid the groundwork for the scientific revolution centuries later. Thinkers like Isaac Newton and René Descartes integrated philosophical principles into their scientific explorations, emphasizing the role of reason, order, and rationality in understanding the universe. Philosophy has also influenced the scientific method itself, particularly in the realm of epistemology. The work of 20th century philosopher Karl Popper, for example, was instrumental in shaping the way scientists approach theories and hypotheses. Popper's philosophy emphasized the importance of falsifiability as a criterion for scientific theories. That is, a theory must be testable and able to be proven false through experimentation. This principle became a cornerstone of scientific practice, providing a clear framework for how scientific theories are developed, tested, and validated. But science is not just about observation and data. It's also about interpretation. The Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg, highlighted the importance of philosophical reflection in scientific theory. This interpretation posited that physical systems do not possess definite properties until they are observed. The implications of this are profound, suggesting that reality itself may be inherently uncertain or dependent on the observer. This idea challenges our intuitive understanding of the physical world and has sparked deep philosophical debates about the nature of reality, the role of observation in shaping existence, and the limitations of human perception. In many ways, the idea of the multiverse can be seen as a natural extension of these scientific and philosophical discussions. If our understanding of the universe is limited by our cognitive capacities, then the existence of multiple, perhaps infinite universes challenges us to rethink not just the cosmos, but our very place within it. It invites us to ask, what is reality? What are the limits of our knowledge? And perhaps most intriguingly, what lies beyond the universe we know? Thus, the multiverse theory is not merely a scientific hypothesis. It is a philosophical and metaphysical inquiry that pushes the boundaries of human understanding. It intertwines the scientific quest for knowledge with the profound questions of existence, space, and reality. And in doing so, it invites a richer, more complex exploration of the universe, one that continues to inspire awe and wonder. Philosophical inquiry into the fundamental nature of reality often serves as the driving force behind scientific exploration. In fact, questions about the origin, structure, and ultimate fate of the universe are as deeply rooted in philosophy as they are in science. Theories such as the Big Bang Theory, general relativity, and quantum mechanics not only address empirical phenomena, but also engage with metaphysical questions about the nature of existence, time, and space. For example, Albert Einstein's theory of general relativity, which describes the curvature of space-time caused by mass and energy, was significantly influenced by his philosophical views on the nature of time and space. Einstein, deeply inspired by Kantian philosophy, believed that space and time were not just passive stages for events to unfold, but active, dynamic elements that shaped the reality we experience. His theory of relativity fundamentally reshaped our understanding of the cosmos, blending scientific and philosophical ideas into one revolutionary framework. Philosophy, however, doesn't just shape the theories we use to understand the universe. It also plays a vital role in guiding ethical considerations within science. As scientific advancements push forward, especially in fields such as nuclear technology, genetic engineering, and artificial intelligence, ethical frameworks derived from philosophy are essential in guiding the responsible application of new knowledge. For example, the ethical dilemmas posed by cloning or the potential consequences of AI on society require deep philosophical inquiry to ensure that these advancements benefit humanity without compromising our moral values. Philosophical perspectives also intersect with science through thought experiments, mental exercises that help us explore complex theories. These thought experiments, often initiated by philosophers, have been adopted by scientists to probe the limits of human understanding. One such famous thought experiment is Schrödinger's cat, a paradox that questions the nature of quantum superposition and the role of observation in determining reality. Similarly, Einstein's thought experiments, such as his consideration of riding alongside a light beam, helped shape the conceptual foundation of his theory of relativity. These mental exercises challenge us to think in new ways, refine our theories, and sometimes uncover groundbreaking scientific insights. In a similar vein, the philosophical critique of quantum mechanics by Einstein and his colleagues, Boris Podolsky and Nathan Rosen, famously led to the Einstein-Podolsky-Rosen (EPR) paradox, which questioned the completeness of quantum theory. This philosophical challenge to science sparked new avenues of investigation and eventually led to the discovery of quantum entanglement and the formulation of Bell's theorem. These theoretical advances, driven by the interplay between philosophy and science, have forever changed how we understand the microscopic universe. Such intersections between philosophy and science are essential in our search for the truth about the universe. Philosophy helps lay the groundwork for scientific methodologies, providing essential concepts that guide our interpretation of empirical data. It pushes the boundaries of scientific theories by asking questions that challenge not only the scope of human knowledge, but the very nature of reality itself. This dynamic interplay fosters a more robust and nuanced understanding of the universe, highlighting the importance of interdisciplinary thinking in the quest for knowledge. Now imagine for a moment the awe-inspiring thought of reaching the edge of the universe. What would you find there? It's a mind-bending question that stretches the limits of human imagination, taking us to the outermost frontiers of both science and philosophy. According to the prevailing scientific theory, the universe is continuously expanding, like an inflating balloon. Each galaxy represents a tiny dot on its surface. If you were to travel far enough, you might think you would encounter the edge, but instead, you would find yourself looping back upon itself, just as if you were traversing the surface of a sphere. The idea that the universe could be finite yet unbounded challenges the very concept of boundaries, forcing us to reconsider our understanding of space and existence. This raises existential questions of profound depth. If the universe truly has no edge and is infinite in its nature, where do we as individuals fit into this vast cosmic expanse? Are we merely an insignificant speck in an endless ocean of stars, or do we hold some greater significance within this grand structure? Conversely, if there are boundaries to the universe, or perhaps even other universes within a multiverse, does that imply the existence of alternate realities, perhaps even versions of ourselves living different lives? These possibilities stretch the imagination and challenge the very meaning of existence itself. The act of contemplating the edge of the universe not only forces us to confront the limitations of our knowledge, but compels us to examine the fundamental nature of reality. This search for the edge of the universe is not just about the quest to map the cosmos. It's also about expanding our minds, pushing the limits of both science and philosophy. As we delve deeper into the universe's mysteries, our understanding of reality is forced to evolve, transcending the boundaries of current knowledge. Looking outward into the vast expanse, we have our current observational technologies, the Hubble Space Telescope and the new James Webb Space Telescope, each an incredible technological marvel. These instruments allow us to capture breathtaking images of the cosmos, bringing us closer to the farthest reaches of the universe. Yet even these advancements have their limits. The furthest object observed by any telescope is about 13.4 billion light-years away. While this is an astonishing distance, it still represents only a tiny fraction of the observable universe. In truth, the more we discover, the more we realize how little we actually know, and how much remains to be explored. The boundaries of the universe may be beyond our reach, but the pursuit of knowledge continues to propel us forward, with both scientific and philosophical curiosity guiding the way. The search for the universe's edge is a profound journey, a journey that is as much about exploring the cosmos as it is about understanding our place within it. As science and philosophy continue to evolve, they will undoubtedly lead us to deeper insights, unlocking the mysteries of reality one discovery at a time. The finite speed of light means we're essentially peering into the past, glimpsing celestial objects as they appeared eons ago. This fundamental limitation shapes everything we observe in the universe. It's as if we're chasing shadows, unable to fully grasp the present state of distant stars and galaxies, and this insight, although profound, reveals a universe that is both awe-inspiring and frustratingly elusive. Yet the challenges do not end there. Another critical obstacle is that the pervasive cosmic background radiation, a lingering remnant from the Big Bang itself. This radiation acts like a foggy veil, obscuring our view of the universe beyond a certain point, making it virtually impossible to observe anything earlier than around 380,000 years after the universe's birth. Thus, even with our most advanced tools, we're restricted in how far back we can peer into the cosmos. But the boundaries of exploration are not confined to the distant past alone. At the very edge of our understanding lies the enigmatic realm of dark matter and dark energy, mysterious forces that account for approximately 95% of the universe's total mass energy content. Despite their dominance in shaping the universe's structure and expansion, these phenomena remain virtually invisible to our instruments. We detect their influence through the gravitational pull they exert on visible matter and their role in the accelerating expansion of the universe. But direct observation remains out of reach. It's a tantalizing enigma that calls for breakthroughs in both theory and technology. Moreover, we face immense observational challenges when dealing with objects like black holes and neutron stars. These extreme environments are defined by their incredibly dense nature, warping both space and time in ways that are difficult to measure. Our current methods rely on indirect observations, gravitational waves, X-rays, and radio emissions, and computer simulations to provide us with an understanding of their behavior, but direct measurement is still beyond our grasp. In this pursuit, we continue to push the limits of both our instruments and our imagination, striving to unlock the secrets hidden in the darkest corners of space. The quest for deeper knowledge is not without its moments of optimism. As we look to the future, the potential for technological advancements offers a glimpse into a world where the universe becomes more visible, more comprehensible. Imagine a future where space-based interferometry, where multiple telescopes spread across vast distances in space work in concert, produces highly detailed, unprecedented images of distant celestial bodies. This could allow us to observe exoplanets orbiting faraway stars with such precision that we could detect surface features, weather patterns, and even signs of life. Furthermore, advancements in quantum technology may radically change how we gather and interpret data from the cosmos. Quantum sensors, which could detect even the faintest signals, might allow us to bypass current limitations caused by noise and chaos in universal signals. Meanwhile, quantum communication could lead to more precise measurements, opening doors to clearer understanding. Artificial intelligence and machine learning will play pivotal roles in this transformation, enabling the analysis of vast amounts of data in real time, accelerating the pace of discovery. As we stand at the threshold of these technological advancements, the potential to expand our observable universe becomes ever more tangible. With innovations in material science, propulsion, and even concepts like light sails and nuclear fusion-powered spacecraft, we might soon be able to deploy telescopes to previously unreachable regions of space. The idea of expanding our understanding of the universe, not just in distance but in detail and depth, is not just a dream but an impending reality. Looking outward is also a journey inward, as we face the immense challenges of cosmic distances. Our most distant observations show us objects as they were billions of years ago, shaped by the universe's evolution. This time lag, created by the finite speed of light, complicates our ability to understand the present state of these distant phenomena. It's as though we are trying to chart the course of a ship based only on the waves it created in the distant past. The deeper we look into the universe, the more we are confronted by the constraints of time itself. As the farther we aim our instruments, the more we're limited by the universe's age. And then there's the accelerating expansion of the universe, a force driven by dark energy that challenges our very understanding of space and time. As galaxies move further apart, our attempts to peer into the furthest reaches of the cosmos are met with increasing difficulty. The universe is not only vast, it is stretching away from us at an ever faster rate. This constant expansion makes the task of exploring the universe all the more daunting, yet all the more exciting. The mysteries it holds beckon us, inviting the curious, the brave, and the innovative to continue this endless pursuit. But this constant expansion of the universe stretches light waves, causing them to redshift, shifting them to longer wavelengths. As a result, distant objects become increasingly difficult to detect. Despite technological advancements, our telescopes struggle to capture vital information as it gets stretched out and dimmed. The farther we look, the more challenging it becomes to observe distant galaxies and celestial phenomena. Additionally, the cosmic microwave background radiation, a faint afterglow from the Big Bang, acts as a boundary. It serves as a cosmic smokescreen, obscuring our view beyond it. Traditional telescopes, no matter how advanced, cannot effectively see past this boundary, limiting our exploration of what lies further out in the universe. Furthermore, theoretical and observational gaps pose significant challenges. Our understanding of phenomena like dark matter and dark energy, comprising the vast majority of the universe's content, remains rudimentary. These elusive components have profound effects on the universe's large-scale structure but resist direct measurement. Current mathematical models and simulations can only hypothesize about these unknowns, leaving astronomers and cosmologists in a perpetual struggle to distinguish between observable facts and theoretical constructs. For those studying the edge of the universe, these challenges are monumental, stretching the limits of our technology, understanding, and imagination. It requires a multifaceted approach that brings together the best of human innovation, collaboration, and relentless curiosity, pushing us ever closer to the cosmic horizon. To tackle these monumental challenges, scientists have devised a multifaceted strategy that blends cutting-edge technologies, innovative methodologies, and international collaboration. One promising avenue lies in the deployment of next-generation space telescopes, such as the James Webb Space Telescope. Equipped with advanced infrared capabilities, this telescope can peer through cosmic dust and gas, enabling it to observe the earliest galaxies formed after the Big Bang. By detecting the faint red-shifted light from these distant objects, Webb expands our observational horizon, providing unprecedented insights into the universe's infancy. Another key strategy involves enhancing ground-based observatories with adaptive optics and very large baseline interferometry, VLBI. Adaptive optics systems can correct for distortions caused by Earth's atmosphere in real time, resulting in sharper, more detailed images of distant astronomical objects. Meanwhile, VLBI connects telescopes across vast geographical distances, allowing them to function as a single massive observatory. This approach provides unparalleled resolution, enabling astronomers to scrutinize ultra-faint cosmic phenomena with extraordinary precision. In addition to these optical advancements, scientists are also pioneering the use of gravitational wave detectors like LIGO and its upcoming successors. These instruments listen to the ripples in space-time caused by massive cosmic events, such as colliding black holes or neutron stars. By detecting these ripples, LIGO and its successors offer a novel way to explore the universe, capturing information that traditional telescopes cannot. International cooperation plays an equally crucial role in this effort. Projects like the Square Kilometer Array, SKA, which aims to create the world's largest radio telescope network, rely on collaboration between countries and institutions. By pooling resources and expertise from around the globe, the SKA promises to drastically improve our capacity to map the universe, study dark energy, and even search for extraterrestrial intelligence. In the face of these challenges, astronomers, physicists, and cosmologists continue to push the boundaries of human knowledge. The quest to understand the universe's edge may seem daunting, but with each breakthrough, we inch ever closer to unraveling the deepest mysteries of the cosmos. Last, advancements in computational astrophysics, driven by the immense capabilities of supercomputers and artificial intelligence, hold the key to unlocking deeper insights into the cosmos. These technological breakthroughs promise to simulate cosmic events with remarkable precision and decipher the massive datasets that astronomers and physicists grapple with every day. By harnessing the power of AI and supercomputing, scientists are not only refining our understanding of the universe's vast complexity, but they are also pushing the boundaries of human knowledge, bringing us ever closer to uncovering the mysteries that lie at the very edge of the known universe. The potential discoveries awaiting us are both exhilarating and awe-inspiring. One of the most tantalizing prospects on the horizon is the direct detection of dark matter, an elusive substance that accounts for roughly 27% of the universe's mass energy content. Although we have yet to observe dark matter directly, its existence is inferred from its gravitational effects on visible matter. Should future experiments successfully identify dark matter particles, it would mark a paradigm shift in our understanding of the universe, offering critical insights into its very structure and revealing what lies beyond the observable horizon. Equally groundbreaking is the tantalizing possibility of discovering proof of the multiverse, an idea that challenges the very nature of reality. Theories in quantum mechanics and cosmology, such as the inflationary model, suggest that our universe may be just one of many, existing in a vast multiverse. If we were to find concrete evidence of other universes, perhaps by detecting anomalies in the cosmic microwave background or gravitational waves, it would completely redefine our perception of existence. No longer would we be searching for the edge of a single universe. Instead, we would confront the idea of infinite, parallel realities, each with its own laws of physics and potential for life. In addition, advancements in particle physics, especially through high-energy experiments at the Large Hadron Collider, LHC, may soon uncover evidence of new dimensions. These experiments probe the fundamental particles and forces that govern the universe, and they might provide answers to some of the most perplexing questions in physics. The discovery of extra dimensions beyond the familiar 3 spatial and 1 temporal dimensions we experience could help explain phenomena like the accelerated expansion of the universe. It might also provide new insights into the nature of reality itself, offering us a deeper understanding of how the universe operates at its most fundamental level. Furthermore, we are witnessing a revolution in observational technology. Deep space probes, along with cutting-edge interferometry networks, are enhancing our ability to map the cosmos and detect celestial phenomena that were once beyond our reach. One of the most intriguing concepts in this realm is the theory of cosmic strings, hypothetical one-dimensional defects in space-time that could hold the key to understanding the universe's makeup and its ultimate boundaries. If these cosmic strings exist, they might help explain the fabric of space and time, shedding light on the very nature of the universe itself. These future discoveries will not only redefine where the universe ends, but they promise to revolutionize our understanding of what lies beyond the known cosmos, altering our conception of existence in profound ways. What do you think exists at the edge of the universe? Share your thoughts and ideas in the comments below. If you're fascinated by the wonders of the cosmos, don't forget to subscribe to Starflux for more insights into the mysteries of the universe. Thanks for watching.